Hello there! Tonight we travel further than any human being has ever physically gone, past the planets, past the stars, past the edge of the observable universe itself, to look at the deepest, strangest, most genuinely unresolved mysteries that modern science has discovered in the cosmos. These are not ancient legends or fringe theories. They are real puzzles being worked on right now by some of the most rigorous minds in physics and astronomy, and they are unresolved because the universe turns out to be far stranger than anyone expected. Before we begin, take a moment to like the video and subscribe, and tell me in the comments where you are listening from and what time it is for you. The visuals you see are just for enjoyment. They are not necessary to follow along. This video is meant to be heard in the background, whether you are studying, resting, or getting ready to sleep. Now let's begin. There is a particular feeling that comes from looking at the night sky for long enough. Not just glancing up at it, actually lying back and watching it, letting the eyes adjust until fainter stars begin to appear in the spaces between the bright ones, until the band of the Milky Way becomes visible as something more than a pale smudge, until the sky stops looking like a flat ceiling with lights and starts revealing itself as a depth, a space, an actual third dimension opening above you into something vast and dark and incomprehensibly large. In that moment, a very specific thought tends to arrive. We know almost nothing about this. It is not exactly a comfortable thought, but it is an honest one. The universe turns out to be made mostly of things we cannot see and cannot directly detect. The forces governing its large-scale behavior are not fully understood. The origins of its structure are partly explained and partly mysterious. The conditions that allow life to exist within it appear to be extraordinarily specific, without a complete explanation for why they are that way. Tonight we look at 30 of these mysteries, specific, deep, genuinely unresolved questions that sit at the heart of our understanding of the cosmos. The questions that keep physicists and astronomers up at night. We begin with the largest structure anyone has ever proposed the existence of. Mystery 1. The cosmic web and the great voids. Picture the universe from the largest possible scale, not from Earth, not from the Milky Way, not even from outside our local group of galaxies, but from so far away that individual galaxies are no longer distinguishable as separate objects, that what you see instead is the overall pattern of matter distributed across the cosmos. At that scale, something remarkable becomes visible. The universe is not a uniform soup of evenly distributed matter. It is a web. Long filaments of galaxy clusters stretch across hundreds of millions of light years, connecting at dense nodes where the richest concentrations of galaxies exist. Between these filaments lie enormous empty regions, the cosmic voids, where almost nothing exists, not fewer galaxies, almost none. Regions spanning hundreds of millions of light years across in which the universe is, by normal standards, essentially empty. The overall pattern looks, when mapped in 3 dimensions, remarkably like a sponge, or like the foam of bubbles, or, and this comparison has been noted by enough scientists to have appeared in serious papers, like the large-scale structure of a neural network. This structure is called the cosmic web, and its existence is explained, at least in outline, by modern cosmological models. After the Big Bang, tiny quantum fluctuations in the density of the early universe were amplified by inflation and then by gravity, causing matter to clump progressively over billions of years into the filamentary structure we observe today. Computer simulations of this process, run on some of the most powerful supercomputers in the world, incorporating the known physics of dark matter, dark energy, and ordinary matter, produce cosmic web structures that match observations impressively well in their general character. But the specific details of the cosmic web continue to produce surprises. Structures have been found that are, by the predictions of those same computer models, too large to have formed in the time available since the Big Bang. The Hercules Corona Borealis Great Wall, a structure identified through observations of gamma-ray bursts, is estimated to span roughly 10 billion light-years, which is a significant fraction of the entire observable universe. At that scale, the cosmological principle, the assumption that the universe is statistically uniform when viewed on large enough scales, begins to show cracks. The cosmological principle is not merely an aesthetic preference. It is a foundational assumption built into the mathematical framework of modern cosmology. If the universe has genuine large-scale structure at the scales these observations suggest, then the standard models need revision, not replacement. The Big Bang, dark matter, and dark energy remain strongly supported by the full body of evidence, but revision in ways that have not yet been worked out. The voids, meanwhile, present their own puzzle. They are not completely empty. The census of galaxies in void regions shows that while galaxy density is dramatically lower than in filaments, it is not zero. And the specific distribution of what is in the voids, the patterns in which the sparse galaxies within them are arranged, carries information about the history of the universe's expansion and the nature of dark energy. Measuring void properties precisely is now one of the strategies being used to test cosmological models and potentially to distinguish between different theories of dark energy. The emptiest regions of space turn out to be scientifically among the most informative. The cosmic microwave background, the faint remnant radiation from the Big Bang, the oldest light in the universe, a photographic record of conditions roughly 380,000 years after the universe began, shows a large, cold spot in the southern sky that has attracted sustained attention. The spot is colder than its surroundings by an amount that is statistically anomalous. Not so anomalous that it definitely requires a new explanation, but unusual enough that it has prompted genuine research into whether it might indicate something physically special about that region of space. One candidate explanation is a supervoid, an enormous underdense region between Earth and the distant surface of last scattering from which the cosmic microwave background originates. When photons cross a void, they gain energy as they enter it and lose energy as they exit it. And if the void is changing in size due to the expansion of the universe, the exit loss is slightly larger than the entry gain, producing a slight cooling effect. A supervoid of sufficient size and depth could potentially account for the cold spot. The evidence for such a supervoid in the relevant direction is suggestive, but not conclusive. The cold spot remains unexplained. Mystery 2. Dark matter. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a large cluster of galaxies located about 320 million light-years from Earth, and noticed that something was wrong. The galaxies in the cluster were moving. That by itself was expected, but they were moving too fast. Much too fast. The logic was straightforward. The total mass of a gravitationally bound system on a cluster of galaxies, a solar system, a star, determines how fast objects within it can move before gravity loses its grip and they escape. Measure the mass, predict the maximum speed. The mass Zwicky could measure, the combined light output and estimated stellar mass of all the galaxies in the Coma cluster, predicted velocities far lower than what he observed. The galaxies were moving at speeds that should have sent them flying apart billions of years ago, and yet there they were, bound together, behaving as though surrounded by far more mass than was visible. Zwicky proposed that most of the cluster's mass was, in some form he called dark matter, matter that did not emit or reflect light, but that contributed to the gravitational binding of the system. At the time, the idea attracted little serious attention. It sounded too speculative. 40 years later, Vera Rubin made the observation that changed cosmology. Working with her collaborator Kent Ford, Rubin measured the rotational velocities of stars in spiral galaxies, how fast stars at different distances from the galactic center were moving around it. According to standard gravitational physics, stars farther from the center should move more slowly, just as the outer planets of the solar system orbit more slowly than the inner ones. Mars moves more slowly than Earth. Saturn moves more slowly than Mars. The pattern is a direct consequence of the inverse square law of gravity. But Rubin found flat rotation curves. Stars at the outer edges of galaxies were moving at essentially the same velocity as stars much closer to the center. This was not a small discrepancy. It was a dramatic one, consistent across every spiral galaxy she measured. The only way to produce a flat rotation curve is to have mass distributed throughout the galaxy extending far beyond the visible disk, a massive, invisible halo surrounding each galaxy. contributing gravitational pull to the outlying stars without emitting any detectable radiation. The evidence for dark matter has accumulated enormously since Rubin's work. Gravitational lensing, the bending of light from distant objects by the gravity of intervening mass, consistently reveals more mass than is visible in galaxy clusters and individual galaxies. The cosmic microwave background contains acoustic oscillations, ripples in the early universe's density, whose pattern is exquisitely sensitive to the ratio of dark matter to ordinary matter, and the pattern observed matches models containing roughly 5 times as much dark matter as ordinary matter. The large-scale structure of the cosmic web, those filaments and voids we described in the previous section, cannot be reproduced in computer simulations without dark matter to act as the gravitational scaffold around which ordinary matter accumulates. Dark matter is as well established as almost anything in modern cosmology. What is not established, what remains one of the deepest open questions in physics, is what dark matter actually is. The leading candidates have been searched for with extraordinary thoroughness. Weakly interacting massive particles, known as WIMPs, were for decades the theoretically preferred candidate. They emerged naturally from supersymmetric extensions of the standard model of particle physics, had the right mass range to produce the observed dark matter abundance, and interacted weakly enough with ordinary matter to have been invisible so far while still being detectable in principle in sufficiently sensitive experiments. Detector after detector was built, progressively more sensitive, progressively more careful to eliminate background noise. None of them found WIMPs. This is not necessarily fatal to the WIMP hypothesis. The parameter space is large and some regions remain unexplored. But the absence of a positive detection in the most sensitive experiments built so far is significant. Other candidates have been proposed and investigated. Axions, hypothetical particles predicted by a different extension of the standard model, much lighter than WIMPs. Sterile neutrinos, hypothetical heavier relatives of the known neutrinos that do not interact even through the weak nuclear force. Primordial black holes that might have formed from density fluctuations in the very early universe before any stars existed, and that might account for some or all of the dark matter through their gravitational effects. Each of these has its advocates and its active search programs. None has been confirmed. There is also a minority position in the physics community that takes the absence of a dark matter particle detection seriously enough to question whether the dark matter hypothesis itself is the right approach. Modified gravity theories that propose the gravitational force law itself is different from what Newton and Einstein described, particularly at the low accelerations characteristic of galactic dynamics, can in some cases reproduce the observed rotation curves without invoking invisible mass. These theories have not succeeded in explaining the full range of evidence as naturally as dark matter models do, particularly the cosmic microwave background power spectrum and the precise details of large-scale structure formation. But they remain active research programs pursued by a small number of serious physicists who are not satisfied that the case for dark matter particles is closed. Whatever dark matter is, the implications of its dominance are staggering. Roughly 84% of the matter in the universe is in a form that emits no light, reflects no light, and has so far resisted every direct detection attempt. The stars and galaxies that light up the night sky, everything that has ever been seen through a telescope or photographed from space, are a minor constituent of the matter sector of the universe, floating like visible foam on an invisible dark ocean. Mystery 3. Dark energy. 3. Dark. In 1998, 2 independent teams of astronomers were engaged in a systematic survey of Type Ia supernovae, a specific class of stellar explosion that produces a consistent peak luminosity, making these explosions reliable, standard candles for measuring cosmic distances. By comparing the apparent brightness of distant supernovae with their known intrinsic luminosity, astronomers can determine how far away they are. And by measuring the redshift of the light from these supernovae, the stretching of wavelengths as the expanding universe carries the source away from the observer, They can determine how fast the universe was expanding when the light was emitted. The experiment was designed to measure the deceleration of the universe's expansion. It was understood that gravity must be slowing the expansion down. The question was how much. The answer would tell physicists what would happen in the long run. A universe that decelerated enough would eventually halt its expansion and recollapse. One that decelerated less would expand forever. The two teams found deceleration all right. Negative deceleration. The universe was not slowing down, it was speeding up. The distant supernovae were dimmer than expected. They were farther away than the expansion rate of the local universe would predict, because the expansion was faster in the past, not slower. The universe was accelerating its expansion. This was one of the most surprising results in the history of cosmology. It was so surprising that the teams initially suspected systematic errors in their measurements. They checked and rechecked. The result held. The Nobel Prize in Physics was awarded for the discovery in 2011. The acceleration required an explanation, and the explanation that has stuck, without being well understood, is dark energy. Something is causing the expansion of space itself to accelerate. Something that acts like a pressure pushing outward, opposing gravity on cosmic scales with an energy density that does not dilute as the universe expands. The simplest version of dark energy is Einstein's cosmological constant, a term he originally introduced into his equations of general relativity to produce a static universe, then removed when the expansion of the universe was discovered, and that has now been resurrected to account for the accelerating expansion. The cosmological constant corresponds to a fixed energy density of empty space itself, a vacuum energy that is present everywhere, always, unchanging. The cosmological constant fits the current data well. The problem is not that it does not fit. It is that no one knows why it has the value it has. Quantum field theory, the framework that describes particles and forces at the microscopic level, predicts that empty space should have an enormous vacuum energy arising from the constant quantum fluctuations of fields throughout space. The predicted value is many orders of magnitude larger than the observed value of the cosmological constant. This discrepancy between the enormous vacuum energy that quantum theory predicts and the tiny but non-zero dark energy that observation reveals is one of the most significant unsolved problems in theoretical physics. It is not a small discrepancy. It is a discrepancy of approximately 120 orders of magnitude, a number so vastly different from the observed value that saying the prediction is wrong understates the situation dramatically. Alternative theories of dark energy, models in which the dark energy density varies over time rather than being a constant, models involving new fields permeating the cosmos, models in which general relativity itself breaks down on cosmic scales, are actively being tested by current and future surveys. The Euclid Space Telescope, launched in 2023, is designed specifically to map the distribution of galaxies and galaxy clusters with sufficient precision to distinguish between different dark energy models. The Dark Energy Spectroscopic Instrument on the ground is doing the same. Results from these surveys over the coming years may narrow the range of viable dark energy theories significantly. What they are unlikely to do is explain where the dark energy comes from. Whatever its physical origin, dark energy makes up approximately 68% of the total energy content of the universe. Combined with dark matter at 27%, the familiar ordinary matter of atoms, stars, and planets accounts for only about 5% of reality. The cosmos is dominated by two invisible, poorly understood components, and all of human history, all of science and civilization and observation has been conducted using only the 5% that is accessible to direct investigation. Mystery 4. The Hubble tension. Measuring the expansion rate of the universe sounds like the kind of thing that, once done carefully enough, should produce a definitive answer. The expansion rate, expressed as the Hubble constant in units of kilometers per second per megaparsec, tells you how fast the universe is expanding, specifically how much faster a galaxy 1 megaparsec away is receding from us compared to one that is 2 megaparsecs away. Measure this number precisely, and you have a fundamental parameter characterizing the universe's current state. The problem is that two fundamentally different methods of measuring the Hubble constant are producing different answers, and the discrepancy has grown large enough to be statistically significant, to the point where most astronomers now believe it is unlikely to go away with better measurements. It is more likely telling us something real about the universe that we do not yet understand. One method uses the cosmic microwave background, the ancient relic radiation from the Big Bang. The pattern of temperature fluctuations in the cosmic microwave background is sensitive to the cosmological parameters, including the Hubble constant. Fitting the observed pattern with the best fit cosmological model, a procedure done with extraordinary precision by the Planck satellite, yields a Hubble constant of approximately 67 kilometers per second per megaparsec. The other method uses distance indicators in the local universe. The cosmic distance ladder, built from parallax measurements of nearby stars, to Cepheid variable stars whose period luminosity relationship calibrates their distances, to type Ia supernovae that use the calibrated Cepheid distances to extend measurements to cosmological distances. This entirely independent approach consistently yields a Hubble constant of approximately 73 kilometers per second per megaparsec. The difference is about 9%, and it has been measured with enough care by multiple independent groups using different techniques that systematic error is becoming an increasingly implausible explanation. The Hubble tension, as it is known, appears to be real, and if it is real, it means either that the standard cosmological model is missing something important, or that both methods are correct, and the universe genuinely expanded at different rates, in different epochs, in ways the standard model does not predict. Proposed solutions to the Hubble tension include modifications to the physics of the early universe, additional relativistic species in the early cosmos, new interactions between particles, early dark energy that slightly altered the pre-recombination expansion rate, and modifications to the late universe, including changes to how dark energy behaves or alternative gravity theories. None of these proposals has achieved broad acceptance, partly because they tend to solve the Hubble tension at the cost of worsening the fit to other cosmological observations. The tension remains unresolved, and it is one of the most actively discussed problems in contemporary cosmology. Mystery 5: The Wow Signal and the Silence of the Universe. On the night of August 15, 1977, the Big Ear radio telescope at Ohio State University was conducting a systematic survey of the sky as part of the Search for Extraterrestrial Intelligence program. The telescope swept across the sky continuously as Earth rotated, printing out observations on long paper printouts that were reviewed by hand. Astronomer Jerry Amon was reviewing the printout when he noticed something extraordinary. A signal lasting approximately 72 seconds, the time it took the telescope's beam to sweep across a point source, had appeared in a frequency range near the hydrogen line at 21 centimeters, a region of the electromagnetic spectrum that SETI researchers had long considered a logical choice for interstellar communication because hydrogen is the most abundant element in the universe. The signal was strong, narrow band, and appeared to originate from a specific direction in the constellation Sagittarius. Amon circled it in red ink and wrote "Wow" in the margin. That annotation gave the signal its permanent name. It has been studied ever since, and it has never been adequately explained. The wow signal has never repeated. Searches directed toward the same region of sky, conducted repeatedly over the decades since, have found nothing comparable. This non-repetition is the most significant argument against an extraterrestrial intelligence origin. A transmitting civilization would, most analyses suggest, be transmitting continuously rather than in a single isolated burst. Natural explanations have been proposed, including a hydrogen cloud, a comet, or a radio frequency interference event, but each of these has difficulties. Hydrogen emission from comets was proposed in 2016 as an explanation, and the specific comets in the vicinity at the time were identified as candidates, but this hypothesis has not achieved wide acceptance among astronomers who have analyzed the signal's characteristics in detail. The WOW signal remains classified as unexplained. It is not confirmed as evidence of extraterrestrial intelligence. The evidence for that conclusion is nowhere near sufficient. But it is also not confirmed as a natural phenomenon. It sits in a category that is genuinely uncomfortable for science, a real, measured, documented signal with no accepted explanation from a direction in the sky that has not produced anything comparable in the 47 years of searching that followed. The silence that surrounds the WOW signal, the silence of the 4.5 decades since that 72-second detection, is itself one of the deepest mysteries in modern astronomy. Mystery 6. The Fermi Paradox. The Italian-American physicist Enrico Fermi reportedly posed the question at a lunch conversation in 1950. The exact words are uncertain. The account has been reconstructed from the memories of those present. But the essence of what he said was something like, if there are so many stars and so many planets, and the universe is so old, where are all the aliens? The logic behind the question is deceptively simple. The Milky Way contains somewhere between 100 and 400 billion stars. Surveys by the Kepler Space Telescope and subsequent instruments have established that most stars have planets, and that a significant fraction of those planets orbit in the habitable zone, where liquid water could exist on the surface. Estimates vary, but there may be tens of billions of potentially habitable planets in our galaxy alone. The Milky Way is approximately 10 billion years old. Life appeared on Earth roughly 4 billion years ago, suggesting that the process of life arising is not impossibly slow on cosmic timescales. If life is common, and if intelligence is a natural endpoint of biological evolution, given sufficient time, then the galaxy should be full of civilizations. Many of them should be far older than humanity, perhaps by hundreds of millions of years. A civilization that old, with a technology trajectory even vaguely resembling humanity's but with millions of years of additional development, should have had time to spread across the entire galaxy. And yet there is no evidence of any of this. No confirmed signals. No detected megastructures. No probes. No visitors. The sky is silent. This is the Fermi paradox, and it genuinely deserves to be called a paradox because the two inputs, the apparent abundance of habitable worlds and the absence of any evidence of other civilizations, are both reasonable empirical claims that are difficult to reconcile. The proposed resolutions fall into several broad categories. The first is that life is extraordinarily rare, that while habitable planets may be common, the specific sequence of chemical and biological events that produced life on Earth was so improbable that it may have happened only once, or a handful of times, in the observable universe. This explanation is uncomfortable partly because we have only one example of a biosphere, making it impossible to assess how probable life's origin actually is. The second resolution involves what has been called the Great Filter, a concept articulated by economist Robin Hanson. The Great Filter is the hypothetical barrier that prevents the development of galactic-scale civilizations. It could be the origin of life, the development of eukaryotic cells, the emergence of multicellular organisms, the development of intelligence, the development of technology, or the survival of technological civilizations past some critical threshold. If the Great Filter is behind us, if we are past whatever the hard step is, then humanity is extraordinarily rare, and the silence of the sky reflects our singularity. If the Great Filter is ahead of us, then the silence of the sky is a warning about what is waiting. The third category of resolution suggests that civilizations do exist but are not detectable by current methods, either because they do not communicate in ways we can recognize, because they deliberately avoid contact, because the distances and timescales of interstellar communication make interaction practically impossible, or because advanced civilizations tend to migrate to computational substrates whose energy signatures are invisible to current technology. The Fermi paradox has no agreed solution. It is one of the few genuinely deep questions in modern science that is simultaneously about physics, biology, philosophy, and the future of civilization. Every year of continued silence makes it slightly more puzzling, and every new exoplanet discovered in a habitable zone makes the puzzle slightly sharper. Mystery 7. Fast radio bursts. On a night in 2001, the Parkes radio telescope in Australia was recording observations of the sky. The data was archived and stored. 6 years later, when astronomer Duncan Lorimer and his student David Narkovic were searching through that archived data, looking for pulsar signals, they found something they had not expected: an intense burst of radio waves lasting only a few milliseconds that showed the clear signature of having traveled an enormous distance through intergalactic space. The signature was in the dispersion of the signal. Radio waves of different frequencies travel at slightly different speeds through the diffuse plasma of intergalactic space, causing higher frequency waves to arrive slightly before lower frequency ones. The amount of this dispersion is proportional to the total column density of electrons the waves have passed through, which in turn depends on the distance traveled. The dispersion measure of the burst Lorimer and Narkovic found implied a source distance of billions of light-years, a source in another galaxy entirely, not in the Milky Way. This was extraordinary, an event billions of light-years away lasting only milliseconds that in that brief span of time released as much energy as the Sun emits in several days. The Lorimer burst, as it came to be known, was the first fast radio bursting, and it took years before the astronomical community was fully convinced that it was a real astrophysical phenomenon rather than a terrestrial interference event. The skepticism was reasonable. Radio frequency interference from Earth-based sources is a constant problem for radio telescopes, and a single detection, archived years before being analyzed, was difficult to verify. More FRBs followed. As new radio telescopes with better interference rejection were built, detections accelerated. Hundreds of FRBs have now been identified, and a new one is detected somewhere in the sky approximately every few minutes, though most of this cosmic radio static goes unobserved because no telescope is watching the right part of the sky at the right moment. The events are brief, violent, and distributed across the entire sky in a pattern consistent with their origins in distant galaxies. What produces FRBs remains an active area of research. The leading candidates are magnetars, neutron stars with extraordinarily powerful magnetic fields, among the most extreme objects in the universe. A critical piece of evidence came in 2020 when an FRB-like burst was detected from a magnetar within the Milky Way. The first time an FRB source was unambiguously identified, and the first time the burst was detected simultaneously in both radio and X-ray wavelengths, consistent with the magnetar model. This strongly suggests that at least some FRBs originate from magnetars, but not all FRBs behave identically. Some repeat, producing multiple bursts from the same source. Some show periodic behavior, bursting preferentially at specific phases of an orbital or precessional cycle. Some appear to be associated with very young magnetars in regions of active star formation. Others seem to come from environments inconsistent with very young objects. Whether all FRBs have the same physical origin or whether the category encompasses multiple different phenomena remains debated. What makes FRBs particularly fascinating from a cosmological perspective is their potential as probes of the intergalactic medium. Because the dispersion of an FRB signal depends on the total electron content between source and observer, precise dispersion measurements for FRBs with known host galaxies and known redshifts allow astronomers to measure the electron density of the intergalactic medium with unprecedented precision. This is directly relevant to the question of where the universe's baryons, ordinary atomic matter, are hiding, since a significant fraction of ordinary matter is expected to exist in a diffuse, warm-hot, intergalactic medium that has been difficult to detect by other means. FRBs may turn out to be some of the most useful cosmological tools ever discovered, quite apart from whatever physical processes produce them. Mystery 8. The Antikythera Mechanism of the Cosmos. In 2006, the astronomer John Chambers published a series of computer simulations examining the long-term stability of the solar system. The simulations modeled the gravitational interactions between the planets over billions of years, and they produced an unsettling result. In a small but non-negligible fraction of simulation runs, Mercury's orbit became chaotic, was perturbed by Jupiter into an eccentric orbit, and eventually led to a collision between Mercury and Venus, or a collision between Mars and the Earth. The solar system we inhabit, the simulation suggested, might not be as stable as it appears over the longest timescales. The planetary orbits we experience as fixed and regular are the product of a gravitational balance that is in the deepest sense, contingent rather than inevitable. This connects to a broader mystery about the architecture of the solar system and of planetary systems generally that modern astronomy has revealed. The arrangement of planets in our solar system does not conform to simple theoretical predictions about how planetary systems should form. The inner solar system, 4 small rocky planets, then an asteroid belt, then 4 giant outer planets, matches the general prediction that planets form from a disk of gas and dust around a young star. But the specific configuration, including the sizes, spacings, and orbital characteristics of the actual planets, is not what simple theoretical models would predict if you ran the formation process forward from a generic initial disk. The outer solar system in particular has a history that astronomers have been reconstructing over the past 2 decades. The leading theoretical framework, the Nice model, named for the French city where the key papers were developed, proposes that the giant outer planets originally formed in a much more compact configuration, then underwent a period of orbital instability triggered by gravitational interactions with a remnant disk of small icy bodies beyond their initial orbits. This instability caused the planets to migrate to their current positions and scattered enormous numbers of small bodies both inward, producing the late heavy bombardment observed in the lunar crater record, and outward, creating the scattered disk and Oort cloud. Jupiter and Saturn settled into their current nearly circular orbits. Uranus and Neptune moved outward to their present distances, and the leftover debris of the process became the Kuiper belt. This model explains many features of the outer solar system remarkably well, but it requires fine-tuned initial conditions, and it has difficulty accounting for some specific details of the observed architecture. The solar system looks, on reflection, like a system that has had a complicated history, one that left specific signatures in the arrangement of the planets and small bodies that we are still learning to read. The mystery is not simply about the solar system's past. It is about what the solar system tells us about planetary system formation generally. The exoplanet surveys of the past 2 decades have revealed that other planetary systems have architectures radically different from our own. Many have giant planets orbiting much closer to their stars than Jupiter does. Many have multiple planets in tightly packed configurations with very small orbital separations. The variety of planetary system architectures appears to be enormous, far more varied than the single example of our solar system would have allowed us to predict. The general principles governing why any particular planetary system ends up with the configuration it has are still being worked out. Mystery 9. The information paradox. This mystery begins with a theoretical result that Stephen Hawking arrived at in 1974, and that has occupied some of the most brilliant minds in theoretical physics ever since, without producing a widely accepted resolution. The result is called Hawking radiation, and its implications are more disturbing than its name suggests. The starting point is quantum mechanics applied to the region near a black hole's event horizon. In quantum field theory, what we call empty space is not truly empty. It is filled with quantum fields that constantly fluctuate, briefly producing pairs of virtual particles that almost immediately annihilate each other. Near a black hole's event horizon, Hawking showed that these fluctuations can produce pairs of particles in which one member of the pair falls inside the horizon while the other escapes to infinity. The escaping particle carries energy away from the black hole. Over time, this process slowly depletes the black hole's mass. The black hole radiates and eventually, over an almost incomprehensibly long time, evaporates completely. This result is remarkable for several reasons. It was the first successful calculation to combine quantum mechanics and general relativity in a physical prediction. Hawking radiation sits at the interface between the 2 great theories of 20th century physics, and it makes a specific, testable prediction. Black holes have a temperature inversely proportional to their mass, and they radiate as black bodies at that temperature. For astrophysical black holes, this temperature is ludicrously small, far below the temperature of the cosmic microwave background radiation that fills the universe, so Hawking radiation cannot be directly detected in practice for any known black hole. but the theoretical result is considered robust. The problem, and the information paradox TUNIST, arises from a specific feature of Hawking radiation as originally calculated. The radiation is precisely thermal. It carries no information about the specific quantum state of the matter that formed the black hole or fell into it. From a quantum mechanical perspective, this is catastrophic. Quantum mechanics is built on the principle that information is conserved, that the quantum state of a system at one time determines the quantum state at all future times, and that the process is reversible in principle. If you know the current state of a system completely, you can in principle reconstruct its entire past history. This is the principle of unitarity, and it is foundational to quantum mechanics. A black hole that forms from specific quantum mechanically defined matter and then evaporates by emitting perfectly thermal radiation violates unitarity. Information is lost. The specific details of what formed the black hole are gone once it evaporates. But quantum mechanics says information cannot be lost. Therefore, either quantum mechanics is wrong, or general relativity as applied to black holes is wrong, or Hawking's original calculation missed something important about how the radiation actually works. Hawking himself initially argued that information was genuinely lost in black hole evaporation, that quantum mechanics needed to be modified to accommodate this possibility. Most other physicists disagreed and continued searching for a resolution within standard quantum mechanics. Over the subsequent decades, the majority of theoretical physicists came to believe that information must be preserved somehow, that it is encoded in subtle quantum correlations in the Hawking radiation that are not visible in the thermal approximation but must be present in the exact calculation. The holographic principle, the idea that the information content of a volume of space is encoded on its boundary surface rather than in its interior, emerged partly as a possible resolution. In this framework, the information about what fell into a black hole is somehow encoded on the event horizon itself, and the Hawking radiation carries that information out in subtle quantum correlations. But the mechanism by which this happens remains unclear. In 2012, a new angle on the problem emerged in a paper by Almheiri, Marolf, Polchinski, and Sully that proposed the firewall paradox. Their calculation suggested that if information is genuinely encoded in the Hawking radiation and escapes the black hole, then the event horizon itself cannot be smooth and empty. It must be a wall of highly energetic radiation that would destroy anything trying to cross it. This directly contradicts general relativity's prediction that an infalling observer would notice nothing special upon crossing the horizon of a sufficiently large black hole. The conflict between the two predictions brought the information paradox back to the center of theoretical physics in a new form. The most recent work on this problem by Pennington and by Almheiri and collaborators around 2019-2020 used tools from holography and quantum information theory to calculate the entanglement entropy of the Hawking radiation over time, finding results consistent with information being preserved, with entropy following what is called the Page curve, rising and then falling, rather than increasing monotonically as it would if information were truly lost. This is considered a significant advance, suggesting that information is indeed preserved, but the physical mechanism by which it escapes the black hole, what specifically carries the information out in the radiation, remains opaque. The information paradox is not merely a technical puzzle in theoretical physics. It sits at the intersection of quantum mechanics and general relativity, and its resolution requires a complete theory of quantum gravity that nobody currently has. The paradox is a symptom of the deeper incompleteness of modern physics. Mystery 10. Neutron stars. When a massive star exhausts the nuclear fuel in its core, gravity wins. The core collapses with extraordinary speed. In less than a second, the inner core of a star, several times the mass of the Sun, compresses to an object perhaps 20 kilometers across. The density achieved in this collapse is extraordinary. A neutron star is so dense that a teaspoon of its material would weigh approximately as much as a mountain. The protons and electrons of ordinary matter are forced together by the enormous pressure to form neutrons, giving the object its name. What happens inside a neutron star, what state matter takes in those extreme conditions, is one of the deepest unsolved problems in nuclear physics. At the densities present in a neutron star's core, matter behaves in ways that cannot be reproduced in any laboratory on Earth. The models used to describe the behavior of matter at these densities, the nuclear equation of state, have significant uncertainties, and different theoretical models make different predictions about the size, maximum mass, and internal structure of neutron stars. One of the key open questions is whether a neutron star's core contains exotic matter not found in ordinary atomic nuclei. At sufficiently high densities, it may become energetically favorable for neutrons to dissolve into their constituent quarks. For the core to consist not of neutrons but of a quark-gluon plasma, a state of matter that last existed in the universe about a microsecond after the Big Bang, and that has been briefly produced in particle accelerators like the Large Hadron Collider. Alternatively, strange quarks, a heavier variety of quark not present in ordinary protons and neutrons, might combine with up and down quarks to form strange quark matter. If strange quark matter is stable in bulk, strange quark stars might exist, objects composed entirely of strange quark matter that are even denser than ordinary neutron stars. The detection of gravitational waves from neutron star mergers, the first such detection, GW17817 in 2017, was accompanied by electromagnetic emission across the entire spectrum, from gamma rays to radio waves, making it the most multi-messenger astronomical event ever observed, has provided new constraints on the nuclear equation of state. The gravitational wave signal carries information about how the neutron stars deformed each other tidally as they spiraled together, and the degree of tidal deformation depends on the equation of state. GW170817 constrained the radius of a typical neutron star to within a few kilometers, significantly narrowing the space of viable equation of state models. But significant uncertainty remains, and the question of what the densest cores of neutron stars contain is still open. The surface physics of neutron stars presents its own set of puzzles. Pulsars, rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles, producing a lighthouse effect as the beam sweeps past Earth, show occasional sudden increases in their spin rate called glitches. These glitches appear to be caused by the transfer of angular momentum from a superfluid component inside the neutron star to the crust. This interpretation implies that part of the interior of a neutron star consists of neutron superfluid, a quantum state of matter in which superfluidity occurs on macroscopic scales. The precise mechanism of pulsar glitches and what it reveals about neutron star interiors remains an active research topic. Magnetars, the specific type of neutron star with the most powerful magnetic fields in the known universe, add another layer to the puzzle. Their magnetic fields can be 1,000 times stronger than those of ordinary pulsars, and the mechanisms by which such extreme fields are generated and maintained are not fully understood. Magnetar flares, sudden releases of enormous amounts of energy from the magnetic field's rearrangement, have been detected from magnetars in the Milky Way and in nearby galaxies, and these events include some of the most energetic phenomena observed in the local universe. One magnetar flare detected in December 2004 from a source called SGR 1806-20 was so energetic that it briefly ionized Earth's upper atmosphere, despite originating 16,000 light-years away. Mystery 11. The matter-antimatter asymmetry. Of all the mysteries in this list, this one is perhaps the most fundamental in its implications, because it is not asking about the structure of the universe or the forces governing it, but about why there is a universe at all rather than nothing. The standard model of particle physics predicts that matter and antimatter should be created in equal amounts in high-energy processes. The Big Bang was a high-energy process of almost incomprehensible intensity, producing enormous numbers of particle-antiparticle pairs in the first fractions of a second of cosmic history. If matter and antimatter were produced in exactly equal amounts, they would have annihilated each other completely, leaving behind only radiation. No protons, no neutrons, no electrons, no atoms, no stars, no galaxies, no anything. The universe would be a featureless bath of photons. We exist. Therefore, something must have produced an asymmetry between matter and antimatter in the early universe. The observed universe contains matter but essentially no primordial antimatter. Antiparticles exist in the modern universe, produced by high-energy processes like cosmic ray collisions or in particle accelerators, but there is no evidence of large regions of the universe composed of antimatter. If such regions existed, they would produce distinctive gamma-ray emission at the boundaries where matter and antimatter met and annihilated. No such emission has been detected on any large scale. The excess of matter over antimatter that allowed the universe to have any matter content at all must have been extremely small, roughly one extra matter particle for every billion matter-antimatter pairs. After the initial annihilation, that tiny excess fraction survived to become everything that exists. The physical process that generated this asymmetry is called baryogenesis, and the conditions it requires were identified by the Soviet physicist Andrei Sakharov in 1967. There must be violation of baryon number conservation, processes that create more baryons than antibaryons, violation of the combined symmetry of charge, conjugation and parity, CP violation, and departure from thermal equilibrium. All three of these conditions can in principle be satisfied within or beyond the standard model of particle physics. The standard model does contain CP violation. The weak nuclear force treats matter and antimatter slightly differently, and this asymmetry has been measured in the decays of certain particles, but the amount of CP violation in the standard model is far too small to account for the observed matter-antimatter asymmetry. Something beyond the standard model must have generated a larger asymmetry in the early universe. This something is unknown. Extensions of the standard model, including various supersymmetric theories and models with additional Higgs bosons, can in principle provide sufficient CP violation. Leptogenesis, a mechanism involving the decays of heavy neutrinos in the early universe generating an asymmetry in leptons that is then converted into a baryon asymmetry, is one of the leading theoretical frameworks. But none of these mechanisms has been experimentally confirmed, and the precise physical process responsible for baryogenesis is one of the most important open questions in both particle physics and cosmology. The matter-antimatter asymmetry is not a small technical puzzle. It is the reason the universe contains anything other than radiation. Whatever physical process tipped the balance, however slightly, however briefly, in the first tiny fractions of a second after the Big Bang, it is the reason stars shine, planets orbit them, and living things evolve to look up at the night sky and wonder. Mystery 12. Ultra-high energy cosmic rays. In 1991, a detector in Utah registered the most energetic particle ever measured arriving from space. The particle, which analysis suggested was a proton, carried approximately 50 joules of kinetic energy. This sounds modest until you consider the scale. It is the kinetic energy of a baseball thrown at about 90 miles per hour, concentrated into a single subatomic particle. A proton carrying this much energy is moving at approximately 99.8% of the speed of light. This particle, subsequently named the "Oh my God" particle for the reaction it provoked among the physicists who analyzed it, was not supposed to be able to reach Earth. In 1966, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin independently calculated that cosmic ray protons traveling through intergalactic space above a certain energy threshold, now called the GZK limit after their initials, would interact with the cosmic microwave background radiation and lose energy relatively quickly. At the energy of the "Oh my God" particle, a proton's mean free path, the average distance it can travel before losing a significant fraction of its energy through these interactions, is only about 50 megaparsecs, roughly 160 million light-years. No known astrophysical accelerator capable of producing such energetic particles exists within that distance from Earth. The source of ultra-high energy cosmic rays, particles arriving at Earth with energies above the GZK limit, remains unknown. The Pierre Auger Observatory in Argentina, the largest cosmic ray detector in the world, has detected many such particles and has found evidence for a weak statistical correlation between their arrival directions and the positions of active galactic nuclei and nearby galaxy groups. But the magnetic fields of the Milky Way and intergalactic space deflect charged particles from their original directions, making it difficult to trace them back to their sources with confidence. The acceleration mechanism that produces cosmic rays at these energies is also unclear. Known astrophysical processes, shock waves in supernova remnants, jets from active galactic nuclei, gamma-ray burst environments, can accelerate particles to high energies, but reaching the highest observed energies requires conditions that push the limits of what standard models predict. The fact that cosmic rays arrive at Earth spanning an enormous range of energies with a spectrum that shows specific features, the Ni at around 1 pet-electron volt and the GZK cutoff at the highest energies, hints at a complex picture with multiple source populations and acceleration mechanisms. What makes ultra-high energy cosmic rays more than an astrophysics puzzle is the window they potentially open onto new physics. At the very highest energies, cosmic rays might be produced by mechanisms involving physics beyond the standard model. The decay of super-heavy dark matter particles, the emission from topological defects in the early universe, or other exotic processes. The signatures of these exotic production mechanisms are being searched for in the arrival direction, composition, and energy spectrum of the highest energy events detected at observatories like Augur and the Telescope Array in Utah. Mystery 13. The origin of cosmic magnetic fields. Every astrophysical object in the universe appears to have a magnetic field. Stars have magnetic fields. The Sun's magnetic field drives the solar wind, powers solar flares, and creates the heliosphere that extends far beyond Pluto. Planets have magnetic fields. Earth's field deflects energetic charged particles, protecting the surface from radiation. Neutron stars have magnetic fields of extraordinary intensity. Galaxies have magnetic fields coherent over kiloparsec scales. Galaxy clusters have magnetic fields extending across megaparsecs. The mystery is where all these magnetic fields came from. A magnetic field can be amplified by a dynamo process. The movement of conducting fluid through an existing magnetic field generates electric currents that reinforce the field, allowing it to grow. This is how Earth's magnetic field is maintained, and why planetary and stellar magnetic fields are, in principle, explicable. But a dynamo requires an initial seed field to amplify. Where did the seed fields come from? The problem deepens when you consider galaxy clusters, where the observed magnetic fields on megaparsec scales are difficult to explain by dynamo processes operating within individual galaxies. These large-scale coherent fields appear to require either that the seed fields were established very early in cosmic history, before galaxies formed, or that some large-scale process has organized field lines across enormous volumes of space. Proposed origins for the seed fields include quantum electrodynamic processes in the very early universe, magnetohydrodynamic instabilities during cosmic phase transitions, processes associated with inflation, and generation by the first generation of stars. None of these mechanisms is definitively established as the source. The observational evidence is insufficient to distinguish between them, partly because the observation of cosmic magnetic fields on the largest scales, the intergalactic medium in voids outside of galaxy clusters, is technically very challenging. The generation and evolution of cosmic magnetic fields across the history of the universe is one of the most important and least resolved questions in astrophysics. Magnetic fields are not a minor feature of astrophysical environments. They are dynamically important in star formation. Magnetic pressure can slow the collapse of gas clouds, in the propagation of cosmic rays, in the launching of jets from active galactic nuclei, and in the evolution of the interstellar medium. Understanding where they came from and how they have evolved is essential for a complete picture of how the universe reached its current state. Mystery 14. Supermassive black holes in the early universe. In 2021, astronomers announced the discovery of a quasar designated J03131806. The quasar, an active galactic nucleus, the luminous central region of a galaxy, powered by matter accreting onto a supermassive black hole, was the most distant ever found at the time of its discovery, seen as it existed only about 670 million years after the Big Bang. And the black hole powering it had a mass of approximately 1.6 billion times the mass of the Sun. Picture what that means. The universe was 670 million years old, barely 5% of its current age. Stars had been forming for only a few 100 million years at most. The Milky Way as we know it did not exist. Galaxies were just beginning to assemble their first large-scale structures. And yet somehow, in this cosmic infancy, a black hole had grown to 1.6 billion solar masses. The problem is one of basic arithmetic applied to astrophysics. A black hole can grow only as fast as matter can fall into it. There is a physical upper limit, called the Eddington limit, on the luminosity of an accreting black hole, set by the point where the radiation pressure of the infalling matter equals the gravitational pull. At the Eddington limit, a black hole can roughly double its mass every few tens of millions of years, starting from a seed black hole of a few hundred solar masses, the mass of a massive star's final collapse, and growing at the Eddington rate for the entire time available before J0313-1806 is observed. You cannot get to 1.6 billion solar masses. There is simply not enough time, even if accretion begins as soon as the first stars form and proceeds without interruption at the maximum possible rate. This problem is not unique to J0313-1806. As telescopes have improved and surveys of the distant universe have become more sensitive, similar massive black holes have been found at progressively earlier cosmic epochs. Each new discovery pushes the constraints tighter. The proposed solutions invoke either heavier seed black holes, formed not from individual stellar collapses but from the direct collapse of massive gas clouds, bypassing the stellar phase entirely and producing seeds of perhaps 10,000 to 100,000 solar masses, or episodes of super Eddington accretion, in which matter falls into the black hole faster than the standard Eddington limit predicts, perhaps sustained by specific geometric configurations of the accretion disk. Both mechanisms are physically plausible in principle, but neither has been directly observed, and the conditions required for each are specific enough that their widespread occurrence is not guaranteed by current theoretical models. The supermassive black holes of the early universe remain one of the most actively discussed problems in observational cosmology. The James Webb Space Telescope, with its ability to observe the universe at redshifts and in wavelength ranges inaccessible to earlier instruments, has already found galaxies at even earlier epochs than J0313-1806, some of them with properties suggesting the presence of black holes that push the timing problem to even more extreme limits. Mystery 15, Planet 9 and the Outer Solar System. Beyond the orbit of Neptune, at distances from the Sun measured in hundreds of astronomical units, one astronomical unit being the Earth-Sun distance, a population of small icy bodies occupies the Kuiper belt and the more distant scattered disk. These objects, collectively called trans-Neptunian objects, represent the debris of the outer solar system, the material that was not incorporated into the giant planets. In 2016, Caltech astronomers Konstantin Batygin and Michael Brown published a paper that rekindled a discussion that had been quiet for decades, the possibility of an undiscovered planet in the outer solar system. Their argument was based on the orbital clustering of a specific set of trans-Neptunian objects in the scattered disk. When the orbital parameters of these objects, their perihelia, the points of closest approach to the Sun, and the orientations of their orbits, are examined, statistically, they appear to cluster in a way that is inconsistent with random distribution. The probability of this clustering occurring by chance, with the known solar system as the only influence, was estimated to be less than 1 in several hundred. The clustering could be explained by the gravitational influence of an undiscovered planet, a body Batygin and Brown called Planet 9, on an elongated orbit taking it hundreds of astronomical units from the Sun at its most distant point. The mass required to produce the observed clustering would be roughly 5 to 10 times the mass of Earth, making Planet 9 a sub-Neptune class planet, smaller than Uranus or Neptune, but substantially larger than Earth. The idea is not unprecedented. Neptune itself was discovered after anomalies in Uranus's orbit suggested an unseen perturber. Mathematical prediction followed by telescopic confirmation is one of the great success stories of Newtonian gravity. But Planet 9 has not been found. Extensive searches of the outer solar system using sensitive wide-field surveys have not detected any object with the predicted properties. This absence of detection does not disprove Planet Nine's existence. The object would be so distant that it would be extraordinarily faint, and covering the full parameter space of its predicted orbit requires dedicated survey time, but it increasingly constrains the allowed region of sky where it might be. An alternative explanation for the orbital clustering involves selection bias, the possibility that the sample of trans-Neptunian objects used in the original clustering analysis is not representative because of observational biases in how and where these faint objects have been detected. Studies of surveys designed to avoid such biases have reached different conclusions about the significance of the clustering. The statistical debate is ongoing. If Planet 9 exists, it represents a major gap in the known inventory of the solar system, a world larger than Earth orbiting unseen in the distant darkness beyond Neptune. If it does not exist, the explanation of the trans-Neptunian orbital clustering will require a different physical mechanism. Either way, the outer solar system appears to contain important information about the solar system's history and structure that has not yet been fully extracted. Mystery 16, the arrow of time. The laws of physics, with one minor exception related to the weak nuclear force, are symmetric with respect to time. Run the equations of mechanics, electromagnetism, or quantum mechanics forward or backward, and they work equally well. A film of two billiard balls colliding and bouncing apart is indistinguishable from the film run in reverse. Both are consistent with Newton's laws. A film of a glass shattering into 100 pieces and falling to the floor is instantly recognizable because running it backward shows something that is physically possible in principle, but that never actually happens: the shards spontaneously assembling into a glass and leaping onto the table. Why is the first film reversible and the second one not? The physics of individual particle interactions is reversible, but the physics of large collections of particles is not in practice. The second law of thermodynamics, entropy increases, is the statement that systems evolve from lower to higher entropy states, from more ordered to less ordered configurations, not because individual interactions are irreversible, but because disordered states vastly outnumber ordered ones. If you start with a glass in one piece, the overwhelming majority of ways its atoms can move led to greater disorder over time. The glass shattering is irreversible not because time itself has a direction, but because the glass's intact state was extraordinarily rare. This explanation, the statistical mechanical account of the arrow of time, is compelling and well established, but it raises a deeper question. If the laws of physics are time symmetric, why was the universe in a low entropy state to begin with? Why did the Big Bang produce a universe in an extraordinarily ordered, low entropy configuration so that the subsequent increase in entropy could give rise to the experience of time flowing in a particular direction? This is the problem of the low entropy initial condition of the universe. It is one of the deepest questions in cosmology and statistical mechanics, and it sits at the intersection of thermodynamics, cosmology, and the philosophy of time. Proposed answers range from the anthropic, we can only exist in a universe with this property because the process of life and consciousness requires a thermodynamic gradient, to the cosmological, inflation naturally produces a low entropy initial state, or the universe cycles through states that periodically reset entropy, or the multiverse contains regions with all possible initial conditions, and we happen to inhabit a low entropy one. None of these answers is fully satisfying, and the problem connects to questions about time itself that remain unresolved. The experience of time flowing in one direction, the asymmetry between past and future that is so fundamental to conscious experience, may be one of the deepest mysteries in physics, not because we cannot describe it, but because we do not fully understand why the universe is arranged to produce it. Mystery 17. Cosmic inflation. The first second of the universe's existence is the most important second in cosmic history, and the one we understand least. In the early universe, matter and energy were compressed to densities and temperatures that no experiment on Earth can reproduce, and the physics governing those conditions involves forces and phenomena that the standard model of particle physics may not fully describe. The dominant theoretical framework for the first fraction of a second is cosmic inflation. a hypothetical period of extraordinarily rapid exponential expansion that occurred perhaps between 10 to the minus 36 seconds and 10 to the minus 32 seconds after the Big Bang. During inflation, space expanded by a factor of perhaps 10 to the 26 or more in a tiny fraction of a second, driven by the energy of a hypothetical field called the inflaton. Inflation is not an arbitrary addition to cosmology. It was proposed to solve specific problems. The horizon problem, why the cosmic microwave background is so uniform across regions that, without inflation, could never have been in causal contact. The flatness problem, why the geometry of the universe is so close to perfectly flat, which requires extremely fine-tuned initial conditions without inflation, and the absence of magnetic monopoles, which grand unified theories predict should have been produced in great quantities in the early universe. Inflation naturally solves all three problems, and, crucially, it makes specific, testable predictions. The most important prediction of inflation is that quantum fluctuations in the inflaton field, stretched to cosmic scales by the exponential expansion, should produce a specific pattern of density perturbations that served as the seeds of today's large-scale structure. These perturbations should be nearly scale invariant, the same amplitude at all length scales, and should follow a specific statistical distribution. The cosmic microwave background observations show exactly this pattern, which is one of the strongest pieces of evidence supporting inflation. But inflation also predicts gravitational waves, ripples in spacetime produced by the exponential expansion of the inflationary era. These primordial gravitational waves would leave an imprint on the polarization of the cosmic microwave background, producing a specific pattern called B-mode polarization. This signature has been searched for extensively but not yet definitively detected. The level of gravitational waves produced depends on the energy scale of inflation, and a non-detection constraints but does not eliminate the range of inflationary models. The deeper problem is that while inflation is strongly supported in its broad outlines, there is no consensus on which specific inflationary model is correct, and there are hundreds of proposed models involving different forms of the inflaton potential and different physical mechanisms for ending inflation. The transition from inflation to the hot, dense Big Bang state, called reheating, is also poorly understood. The specific process by which the inflaton field decayed into the particles and radiation of the standard model, filling the universe with energy and beginning the subsequent radiation-dominated phase, has uncertain details that affect predictions for observable quantities. Most consequentially, inflation appears to be generic in a way that makes it difficult to test. Many different inflationary models make predictions that are observationally indistinguishable from each other with current measurements. The predictive power of inflation, while genuine, is less specific than one would like for a fundamental theory of the universe's earliest moments. Mystery 18. The fate of the universe. The future of the universe on cosmic timescales is determined by a competition between gravity and the expansion driven by dark energy. And because dark energy is not well understood, the outcome is genuinely uncertain. If dark energy is a cosmological constant of a fixed energy density of empty space that does not change as the universe expands, then the expansion of the universe will continue to accelerate indefinitely. Galaxies outside our local group are already receding from us faster than the speed of light due to the expansion of space itself. This does not violate special relativity, which restricts the motion of objects through space rather than the expansion of space itself. Over time, more and more galaxies will cross the cosmic event horizon, the boundary beyond which light can never reach us, and disappear from view. In approximately 100 billion years, all galaxies beyond the local group will have faded from visibility. The observable universe will consist only of the Milky Way and its gravitationally bound neighbors. Over much longer timescales, tens of trillions of years, stars will exhaust their fuel and die. New star formation will cease as galaxies consume their available gas. The era of stars, which began a few 100 million years after the Big Bang and encompasses all of human existence, will end. The universe will enter what cosmologists call the degenerate era, populated by stellar remnants, white dwarfs, neutron stars, and black holes, slowly cooling and fading in an ever-expanding darkness. Over still longer timescales, on the order of 10 to the power of 40 years, white dwarfs themselves may decay if the proton is unstable, as some grand unified theories predict. On timescales of 10 to the power of 67 to 10 to the power of 100 years, black holes will evaporate through Hawking radiation. The last massive black holes in the universe will evaporate, leaving behind only low-energy photons and fundamental particles drifting through a universe grown cold and dark. This scenario, the heat death of the universe, is the most commonly discussed long-range forecast for cosmic evolution. But it is contingent on dark energy remaining constant. If dark energy grows stronger over time, if its density increases as the universe expands rather than remaining constant, the outcome could be the Big Rip. In this scenario, the accelerating expansion eventually becomes strong enough not just to pull galaxies apart, but to tear apart galaxy clusters, then individual galaxies, then solar systems, then planets, then individual atoms. The expansion would overwhelm every force in nature, gravity, electromagnetism, the strong nuclear force, in a final moment of total dissolution. There is no observational evidence that dark energy is increasing in strength, and the Big Rip scenario requires specific properties of dark energy that current observations do not support, but neither is it ruled out. The fate of the universe depends on properties of dark energy that we do not understand well enough to forecast with confidence. A third possibility, the Big Crunch, in which dark energy is eventually overcome by gravity and the universe recollapses, was once a serious candidate for cosmic fate, but is now considered unlikely given the observed accelerating expansion. It would require dark energy to change character dramatically from its current behavior. What is certain is that the universe has a finite future in its current form. The era of stars and planets and the possibility of life is a temporary phase, brief on cosmic timescales, extraordinary in its properties, and not indefinitely sustained. Mystery 19. Consciousness in the cosmos. This is the mystery that sits most uncomfortably at the boundary between science and philosophy, and it deserves to be included because it is not merely a philosophical question. It has genuine connections to fundamental physics that the physics community continues to grapple with. The universe, according to quantum mechanics, evolves according to deterministic equations, the Schrödinger equation, until a measurement is made, at which point the quantum state collapses to a definite outcome with specific probabilities. The measurement problem is the question of what constitutes a measurement. What is special about measurement interactions that they produce definite outcomes when ordinary quantum evolution produces superpositions? Does a measurement require a conscious observer? Does the universe exist in a definite state only when observed? Most physicists reject the idea that consciousness plays a fundamental role in quantum mechanics. The outcomes of quantum experiments do not depend on whether a human being is watching, and quantum mechanics works perfectly well in contexts where consciousness is not present. But the interpretation of quantum mechanics, what the theory is actually saying about the nature of reality, remains deeply contested. The Copenhagen interpretation says there is no reality beyond what is measured. The many worlds interpretation says all outcomes happen in branching parallel histories. The pilot wave theory says particles have definite positions guided by a quantum wave. Relational quantum mechanics says quantum states are relative to observers. Each of these interpretations has serious advocates and each faces serious objections. None is universally accepted. The question of consciousness in the cosmos has a separate, more straightforward dimension, the possibility of life and consciousness elsewhere in the universe. We have discussed the Fermi paradox and the evidence for habitable planets. The deeper question, which is genuinely open, is whether the emergence of consciousness is a common or rare outcome of physical processes. We have one example, the evolution of consciousness on Earth through biological processes over approximately 4 billion years. That single example provides very limited statistical information about how likely consciousness is to arise in a universe with the physical laws we observe. What makes this question specifically cosmological rather than purely biological is the observation that the physical constants of the universe appear fine-tuned for the existence of complexity. If the strength of the electromagnetic force was slightly different, atoms could not form. If the strong nuclear force was slightly weaker, protons could not form stable atomic nuclei. If gravity was slightly stronger, the universe would have recollapsed before stars could form. If slightly weaker, galaxies could not have assembled. The specific values of the constants of physics appear in this analysis to be remarkably consistent with a universe that can support chemistry, stars, planets, and ultimately consciousness. Whether this fine-tuning is evidence of something, a selection effect in a multiverse, a deeper principle constraining the constants, or something else entirely, is one of the most important and contested questions at the boundary of physics and cosmology. The universe appears to have been arranged, or to have arranged itself, in a way that makes the existence of observers possible. Why that should be so is a question that modern science can describe but not yet explain. Mystery. 20. The multiverse. The multiverse is the hypothesis that our observable universe, the roughly 93 billion light-year sphere of space from which light has had time to reach us since the Big Bang, is not the entirety of physical reality, but only one of an enormous or infinite number of separate regions, each potentially with different physical properties, different constants, and different histories. The multiverse is not a single hypothesis, but a family of related ideas that arise from different physical theories. The inflationary multiverse arises from eternal inflation, the observation that in many inflationary models, inflation never completely ends globally. Different regions of space exit the inflating state at different times, each producing a bubble universe with its own Big Bang and its own subsequent evolution. Our observable universe is one such bubble, surrounded by an eternally inflating parent space containing countless other bubbles, each potentially with different physical properties depending on how inflation ended within them. The quantum mechanical multiverse, associated with the many worlds interpretation of quantum mechanics, arises from the claim that every quantum event produces a branching of reality into multiple histories, each containing a different outcome. In this picture, the universe constantly splits into parallel branches, and conscious experience follows one branch, while other versions of the observer follow the others. The string theory landscape arises from the observation that string theory predicts an enormous number of possible vacuum states. Estimates range up to 10 to the 500. Each corresponding to a different set of effective physical constants, different numbers of large spatial dimensions, and different low-energy physics. If eternal inflation populates this landscape by producing different vacuum states in different bubble universes, the result is a multiverse in which the physical constants vary across the collection of universes, and intelligent observers inevitably find themselves in a universe where the constants permit their existence. The multiverse is deeply controversial within physics for a reason that is both philosophical and methodological. It is extraordinarily difficult to test. If the other universes are causally disconnected from ours, if no signal can pass between them, then in what sense do they constitute a scientific hypothesis rather than a metaphysical speculation? Proponents argue that the multiverse arises naturally from well-tested physical theories, inflation, quantum mechanics, string theory, and that if those theories are correct, the multiverse follows as a consequence. Critics argue that a theory cannot be tested by the predictive success of its components if the component that generates the untestable prediction, eternal inflation, the quantum mechanical many-worlds branching, is itself not independently testable. There is one potential observational signature. If bubble universes occasionally collide, the collision might leave detectable imprints in the cosmic microwave background, a specific pattern of temperature distortion that would indicate the past collision with another universe. Searches for such signatures have so far not found convincing evidence. Whether such evidence could ever be decisive is itself debated. The multiverse may be real. If it is, the implications are extraordinary. Every possible history happens somewhere. Every quantum outcome is realized. The specific properties of our universe are one draw from an enormous or infinite set of possibilities. If it is not, the alternative is a universe that exists as a singularity. a single instance of cosmic reality with specific properties whose origins remain unexplained. Mystery 21. The Pioneer anomaly and its resolution. In the 1980s and 1990s, scientists tracking the Pioneer 10 and Pioneer 11 spacecraft, which had been launched in the early 1970s and were now traveling through the outer solar system and beyond, noticed a small but persistent discrepancy. The spacecraft were decelerating very slightly more than could be accounted for by known gravitational forces from the Sun, planets, and other solar system bodies. The anomalous acceleration was tiny, approximately 8 billionths of a meter per second squared. But it was real, it was consistent over many years of tracking data, and it pointed toward the Sun, suggesting a small additional force pulling the spacecraft back. For several decades, the Pioneer anomaly, as it became known, was one of the most discussed small-scale puzzles in astrodynamics and occasionally in theoretical physics. The acceleration was of the right order to be interesting relative to the scale set by the Hubble constant, and some researchers speculated that it might hint at new physics modifying gravity on large scales. The constancy of the anomalous acceleration and its persistence over years of tracking made it more than a simple systematic error. The resolution, when it came, was less dramatic than the speculation had anticipated, but more interesting as an exercise in careful scientific investigation. Detailed modeling of the thermal environment of the Pioneer spacecraft, accounting for the heat radiated by the onboard nuclear power sources, its reflection and re-radiation from different surfaces of the spacecraft, and the resulting tiny but cumulative thrust effect, succeeded in accounting for essentially all of the anomalous acceleration. The Pioneer anomaly turned out to be a radiation pressure effect from the spacecraft's own heat, not new physics. The resolution was satisfying in that it closed a specific puzzle, but the process of resolving it is instructive in its own right. The fact that an anomalous acceleration as small as 8 billionths of a meter per second squared could be measured over decades of spacecraft tracking, and that the physical cause could eventually be traced to the subtle thermal radiation environment of the spacecraft, speaks to the precision of modern astrodynamics. It also speaks to the importance of exhausting mundane explanations before reaching for exotic ones, a principle that governs good science and that distinguishes it from less disciplined speculation. The Pioneer anomaly was an anomaly. It was also, in the end, understood. The universe keeps its deepest mysteries well protected behind layers of things that just turn out to be careful thermodynamics. Mystery 22. Rogue planets. The history of astronomy is, in part, a history of realizing that things we thought were unusual are actually common. Planets seemed like rare companions to stars until surveys showed that most stars have them. Black holes seemed like exotic theoretical objects until they were found at the centers of essentially every large galaxy. The same recalibration is now happening for rogue planets. Worlds traveling through interstellar space, unbound to any star, wandering through the galaxy in cold darkness. The mechanism for producing rogue planets is well understood. During the formation of planetary systems, gravitational interactions between the forming planets and between planets and the disk of gas and dust from which they form can eject planets onto hyperbolic trajectories, flinging them out of the system entirely. Jupiter-mass planets are most easily detected, but likely not most common. Computer simulations of planetary system formation suggest that every forming system may eject several rocky planets of Earth mass or smaller. The ejection process is more efficient for smaller bodies because they interact more violently with the gravitational fields of larger neighboring planets. The question is how many rogue planets there are. Estimates based on early microlensing surveys, observations that rely on the gravitational lensing of background stars by intervening objects, which is sensitive to the mass of the lensing object, suggested that rogue planets of Jupiter-like mass might be as common as stars in the Milky Way. More recent, more careful surveys have revised these numbers downward somewhat, but the basic conclusion that rogue planets are common appears robust. There may be billions of planetary mass objects wandering through the galaxy without stellar parents. The implications for habitability are intriguing. A rogue planet is far from any star and receives no stellar light or warmth. Its surface would be impossibly cold, dozens or hundreds of degrees below zero. But the surface is not necessarily the relevant environment. If a rogue planet is large enough, or if it was formed in a planetary system with a large rocky or icy composition, it may retain geological heat from radioactive decay and initial formation long enough to maintain liquid water in a subsurface ocean, shielded from space by a thick ice crust. If the planet retained a thick hydrogen atmosphere, the greenhouse effect of the hydrogen could also maintain warmer surface temperatures even without stellar heating. Life in such environments, deep within a subsurface ocean sustained by geothermal energy rather than sunlight, could in principle persist for billions of years in complete isolation from the broader cosmos. It would be life that had never seen a star, life in permanent darkness, powered by the slow decay of radioactive nuclei, sustained by chemical reactions in warm water circulating near hydrothermal vents. The prospect is strange. It is also by the logic of known biochemistry and the confirmed existence of life in comparable environments on Earth, not obviously impossible. Mystery 23. Europa and the hidden oceans of the solar system. In the 1970s, when the Voyager spacecraft made their flybys of Jupiter and Saturn, the images they returned of the moons of those gas giants astonished planetary scientists. These were not the small, dead, cratered rocks that the Moon and Mars suggested outer solar system objects would be. They were worlds, strange worlds, each with its own character, its own geology, and in some cases its own apparent geological activity. Europa, Jupiter's fourth largest moon, showed a surface unlike anything else in the solar system. Smooth, with very few impact craters, indicating a geologically young surface covered in a network of long, dark lines and ridges that look like the surface of a cracked eggshell. The ice was clearly being reworked continuously by some process below. Tidal heating from Jupiter's gravitational pull was proposed as the energy source, and subsequent analysis confirmed that the tidal flexing of Europa, the stretching and relaxing of the Moon's interior as it moves in its elliptical orbit around Jupiter, generates sufficient heat to maintain a liquid ocean beneath the ice shell. The ocean is real. Multiple independent lines of evidence now support its existence. The morphology of the surface, the magnetic field measurements by the Galileo spacecraft, which found evidence for an induced magnetic field consistent with a conducting layer, salty liquid water in Europa's interior, and the general geophysical arguments about tidal heating. The ocean is estimated to be approximately 100 kilometers deep, extending beneath an ice shell perhaps 15 to 25 kilometers thick. Europa's ocean contains more liquid water than all of Earth's oceans combined. The question that makes Europa one of the most discussed objects in astrobiology is whether anything lives in it. Life on Earth requires three things: liquid water, chemical energy, and the organic building blocks of biochemistry. Europa's ocean appears to have liquid water. The tidal heating that maintains the ocean also drives geological activity on the seafloor, where hot rock-water interactions likely create hydrothermal vents, similar to those on Earth's ocean floor, that support entire ecosystems of organisms that have never seen sunlight. The organic building blocks may have been delivered by the same meteorites and cometary impacts that delivered them to early Earth. The combination of these three ingredients in Europa's ocean has led many astrobiologists to consider Europa one of the best candidates for extraterrestrial life in the solar system. The Europa Clipper mission, launched in October 2024, is designed to characterize Europa's ocean in detail, measuring the ice shell thickness, the ocean's chemistry, and the geological activity of the seafloor, and to assess its habitability. Its results over the coming years may produce the most important information about the potential for life beyond Earth that humanity has yet obtained. What makes the scientific and philosophical stakes of Europa's investigation so high is what a positive result would mean. If life exists in Europa's ocean, it almost certainly evolved independently from life on Earth. The two bodies have been separate since the formation of the solar system, and there is no plausible mechanism for life to have transferred between them. An independent origin of life, evolved under radically different conditions, would imply that life is not a single, extraordinary accident but a natural consequence of the right chemistry and the right environment. The statistical weight of two independent origins, even within a single solar system, would suggest that the universe is full of life. If nothing is in Europa's ocean, if billions of years of stable chemistry in a warm liquid environment produce nothing biological, that too would be an important result, constraining the ease with which life begins and potentially shifting the weight of the Fermi paradox evidence toward the hypothesis that life is genuinely rare. Mystery 24. The accelerating rotation of galaxies and what lies beyond. We discussed dark matter's most famous evidence, the flat rotation curves of spiral galaxies, in an earlier mystery. But the story of galactic dynamics goes deeper than that, into questions about what controls the behavior of galaxies on their own interior scales, and how the properties of dark matter, halos, relate to the properties of the ordinary matter they contain. One of the most intriguing empirical relationships in observational astronomy is called the radial acceleration relation, sometimes known as the MDAR, for mass discrepancy acceleration relation. The relation, established through careful analysis of rotation curve data from hundreds of galaxies of different sizes and morphologies, shows that there is a remarkably tight correlation between the gravitational acceleration predicted from the observed distribution of ordinary luminous matter alone and the actual observed acceleration at every point in a galaxy. This correlation is astonishing in its tightness. At radii, where the gravitational pull from ordinary matter is high, the discrepancy between observed and predicted acceleration is small. Dark matter makes a small contribution. At radii, where the gravitational pull from ordinary matter is low, the discrepancy is large. Dark matter dominates. The transition between these regimes occurs at a specific acceleration scale of approximately 1.2 times 10 to the minus 10 meters per second squared, a number that appears throughout galactic dynamics with suspicious regularity. The existence of this tight correlation was anticipated by a modified gravity theory called MOND, modified Newtonian dynamics, proposed by Israeli physicist Mordechai Milgram in 1983. In MOAND, below a critical acceleration threshold, gravity becomes stronger than Newton's inverse square law predicts, which in most circumstances eliminates the need for dark matter entirely. MOND successfully predicted the shapes of galaxy rotation curves and the radial acceleration relation before the precise observational data that confirmed them were available. The problem for MOND, the reason it has not displaced dark matter in mainstream cosmology, is that it fails to explain observations on scales larger than individual galaxies. Galaxy cluster dynamics require dark matter even within MOND. The acoustic oscillation pattern in the cosmic microwave background is best explained by dark matter particles, not modified gravity. The large-scale structure of the cosmic web cannot be reproduced without a dark matter component. MOND as a complete cosmological theory does not work. But the fact that MOND works so well on galactic scales, better in some analyses than the standard dark matter model, which requires specific fine-tuning of how dark matter distributes itself relative to ordinary matter, suggests that whatever the correct theory of dark matter is, it must somehow produce the radial acceleration relation as a consequence. Why the distribution of dark matter in galaxies correlates so tightly with the distribution of ordinary matter is not naturally explained by the simplest dark matter models, in which dark matter and ordinary matter interact only through gravity and should therefore distribute independently of each other. Some mechanism appears to connect them, and what that mechanism is remains unclear. Mystery 25. The nature of space itself. General relativity describes gravity as the curvature of space-time, the four-dimensional fabric of reality, composed of three spatial dimensions and one time dimension. In this description, space-time is a smooth, continuous manifold that matter curves and through which matter moves along the straightest possible paths. The picture is extraordinarily successful, making predictions confirmed to extraordinary precision in environments ranging from the solar system to binary pulsars to gravitational wave sources. But there are reasons to suspect that space-time as described by general relativity is not the deepest level of description, that it is an effective, emergent phenomenon arising from some more fundamental underlying structure in the same way that the fluid dynamics of water emerges from the behavior of individual water molecules, with no individual molecule possessing the properties of a fluid. The most direct argument is the incompatibility of general relativity with quantum mechanics. General relativity is a classical theory. It describes smooth, continuous fields in a spacetime that is smooth and continuous. Quantum mechanics is a theory of discrete quanta, of superpositions, of uncertainty. When you attempt to quantize general relativity directly, to treat the gravitational field as a quantum field, in the same way that the electromagnetic field is quantized in quantum electrodynamics, you encounter mathematical difficulties that indicate the theory is incomplete at very short distances, specifically below the Planck length of about 10 to the minus 35 meters. At this scale, quantum fluctuations of spacetime itself would be so violent that the smooth manifold picture breaks down entirely. Various approaches to a quantum theory of gravity propose different structures underlying spacetime. String theory, the most extensively developed framework, replaces point particles with one-dimensional strings vibrating in a 10 or 11-dimensional spacetime, with general relativity emerging from string theory in appropriate limits. Loop quantum gravity proposes that space itself is quantized at the Planck scale, consisting of discrete units of area and volume described by a spin network. Causal set theory proposes that spacetime is fundamentally discrete and that the causal relations between events, which events can influence which others, are the fundamental structure from which continuous spacetime geometry emerges approximately. A particularly fascinating development is the idea, emerging from work on the holographic principle and the AD-S-CFT correspondence in string theory, that spacetime geometry may emerge from quantum entanglement. In this picture, the entanglement structure of quantum information in a lower dimensional system without gravity gives rise to a higher dimensional spacetime with gravity when the correspondence is applied. This suggests a remarkable identification. The geometry of space, the distances and curvatures and topology that general relativity describes, may be encoded in the entanglement structure of quantum fields on boundaries. Space, in this picture, is made of information. What does it mean for space to be emergent? It means that the smooth, continuous manifold of everyday experience and of general relativity is an approximation, valid over a vast range of scales, but breaking down at the Planck scale, where the underlying quantum structure becomes apparent. It means that the question, what is space made of, has an answer that is fundamentally different from smaller pieces of space. And it raises the unsettling possibility that some of the properties of space we take for granted, its three large dimensions, its continuous topology, even the forward direction of time, may be emergent features of a more fundamental underlying description rather than irreducible features of reality. This is one of the deepest open questions in theoretical physics, and its resolution, whenever it comes, will represent one of the most significant scientific advances in human history. Mystery 26. The Shadow of a Black Hole. On April 10, 2019, a collaboration of more than 200 scientists called the Event Horizon Telescope released the first direct image of a black hole, specifically of the supermassive black hole at the center of galaxy M87, located approximately 55 million light-years from Earth and carrying a mass of approximately 6.5 billion times the mass of the Sun. The image showed a bright ring of glowing gas surrounding a dark central region. The shadow of the black hole, the region from which no light can escape. The image was assembled from data taken simultaneously by radio telescopes distributed across Earth, in Chile, at the South Pole, in Hawaii, in Spain, in Mexico, using a technique called very long baseline interferometry that combines the signals from all the telescopes to synthesize the resolution of a telescope as large as Earth itself. The angular resolution achieved was sufficient to resolve features at the scale of the event horizon of the M87 black hole, nearly 12 light-hours in diameter across a distance of 55 million light-years. The image confirmed predictions of general relativity in the extreme gravitational environment near a black hole's event horizon. The shape and size of the shadow matched what Einstein's equations predicted for a black hole of the measured mass. The image was both a triumph of observational technique and a confirmation of theory in a regime where the theory had never before been directly tested. What the image did not reveal is at least as significant. The interior of the black hole, the region inside the event horizon, is invisible by definition, since no light from inside can escape. The singularity at the center, where general relativity predicts infinite density and the breakdown of physics, cannot be seen. The questions about what happens inside a black hole, about the information paradox, about quantum gravity effects near the singularity, none of these are addressed by the image. The Event Horizon Telescope showed us the edge of a black hole. The interior remains as opaque as it was before. In April 2022, the Event Horizon Telescope collaboration released a second image, the first image of the black hole at the center of the Milky Way itself, called Sagittarius A8. The Milky Way's central black hole is much smaller than M87's, approximately 4 million solar masses compared to 6.5 billion, and is much closer, about 27,000 light-years away. These different scales make the imaging problem different in character. Because Sagittarius A is smaller and varies on timescales of minutes while the observation takes hours, the image required sophisticated computational techniques to handle the temporal variability and produce a stable, reconstructed image. The result confirmed that Sagittarius A is indeed a black hole consistent with general relativity, while showing a ring structure similar in geometry to M87's. Future improvements to the Event Horizon Telescope network, the addition of more stations, space-based antennas, higher observing frequencies, will improve the resolution and the temporal sampling, potentially revealing the dynamics of matter spiraling into the black hole on timescales of hours. But the event horizon will remain the ultimate boundary. Whatever happens inside it will not be recorded in any image, however powerful the telescope, however sensitive the detector. Some information about the universe is shielded from us not by technology but by the physics of the universe itself. Mystery 27, Exoplanet Atmospheres and the Search for Biosignatures. When astronomers announced the detection of methane in the atmosphere of exoplanet K2-18b in 2023 using the James Webb Space Telescope, they were careful about what conclusions could be drawn. K2-18b is a planet about 2.5 times Earth's radius, orbiting in the habitable zone of a red dwarf star about 120 light-years from Earth. It is classified as a sub-Neptune or Hycean planet, a world that may have a hydrogen-rich atmosphere and a water ocean beneath it. The James Webb Telescope detected water vapor, carbon dioxide, and methane in its atmosphere. More tentatively, it detected hints of dimethyl sulfide, a molecule that on Earth is produced only by biological processes, specifically by marine microorganisms. The claim was immediately qualified by the scientists who made it. The dimethyl sulfide detection was tentative, the signal-to-noise was low, and abiotic production of dimethyl sulfide, while not common on Earth, cannot be ruled out for different planetary environments. No claim of life detection was made. The announcement was framed as evidence that the atmospheric composition of habitable zone exoplanets can now be characterized by James Webb, opening the road toward genuine biosignature searches. Not that life had been found. This caution is appropriate and reflects the difficulty of the problem. A biosignature is not a single molecule but a chemical disequilibrium, a combination of molecules that could not coexist in the observed concentrations without a continuous source of chemical-free energy which biology provides. Oxygen and methane in significant concentrations simultaneously is the classic example. These two molecules react with each other and would rapidly equilibrate to carbon dioxide and water in the absence of a continuous source. The coexistence of both in significant amounts in Earth's atmosphere is a consequence of photosynthesis, producing oxygen, and methanogenic bacteria, producing methane, and would be recognizable to a distant observer as a biological signature. The search for biosignatures in exoplanet atmospheres is the most direct scientific approach to the question of whether life exists beyond Earth. It is also extraordinarily technically challenging. The signal from an exoplanet's atmosphere is tiny compared to the signal from its host star. A planet transiting its star blocks a small fraction of the star's light. and the atmospheric absorption features in that transmitted light are a small fraction of the already small transit signal. Detecting meaningful chemical abundances in an exoplanet atmosphere requires multiple transits observed with the most sensitive instruments available, and even then, the uncertainties are substantial. James Webb represents a quantum leap in this capability. In its first years of operation, it has detected water, carbon dioxide, methane, and sulfur dioxide in exoplanet atmospheres, characterizing compositions that were entirely inaccessible to previous instruments. The next generation of giant ground-based telescopes, the extremely large telescope being built in Chile, with a primary mirror nearly 40 meters in diameter, will provide additional capability, particularly for direct imaging of exoplanet atmospheres rather than the transit spectroscopy that James Webb primarily uses. The detection of a genuine biosignature and a chemical composition in an exoplanet atmosphere that cannot be explained by abiotic chemistry would be one of the most significant scientific discoveries in human history. It would not be immediate certainty of life because the argument that the composition requires biology would need to withstand scrutiny and alternative abiotic explanations would need to be excluded, but it would be the first empirical evidence that life exists beyond Earth, and the implications would reverberate through science, philosophy, and human self-understanding for centuries. Mystery. 28. Dark matter, halos and the galaxy formation problem. We know that dark matter exists, at least to the extent that something providing the right gravitational effects in galaxies and galaxy clusters must exist. We know approximately how much of it there is. We know some of its bulk properties. It is non-relativistic. It interacts only gravitationally with ordinary matter, or very nearly so, and it forms extended halos around galaxies. What we do not know is what it is, the fundamental physics of the dark matter particle or field. But even setting aside the question of what dark matter is, there are persistent puzzles about how it behaves that complicate the picture in important ways. Computer simulations of structure formation in a universe with cold dark matter, the Standard Model, predict specific features of dark matter halos that are in tension with observations of real galaxies. One tension is the cusp core problem. Simulations predict that dark matter halos should have a sharp central density spike, a cusp, where the density rises steeply toward the center. Observations of dwarf galaxies, which are especially sensitive probes of dark matter halo structure because ordinary matter is a small fraction of their total mass, tend to show evidence for a core, a flattened central density profile rather than a steep cusp. The discrepancy between simulated and observed central density profiles has been known for decades and remains unresolved. A related tension is the too big to fail problem. Simulations of the Milky Way's dark matter halo predict that it should contain many satellite subhalos that are large enough and dense enough that they should have formed galaxies. They are too big to fail at forming stars, but the Milky Way's actual population of observed satellite dwarf galaxies is smaller than the predicted population of large subhalos. Some predicted halos appear to have no corresponding observed galaxy. These tensions could be resolved by processes within ordinary matter. The feedback effects of supernovae and stellar winds, which can eject gas from small galaxies and modify the central dark matter distribution. Or they could indicate that dark matter has properties somewhat different from the purely cold, collisionless model. Warm dark matter, particles with a small but non-zero thermal velocity, would smooth out small-scale structure and produce a different satellite galaxy population. Self-interacting dark matter particles that scatter off each other through some non-gravitational interaction, would naturally produce cores rather than cusps through the redistribution of heat in the inner halo. Neither of these alternatives has been definitively confirmed or ruled out. The detailed comparison between simulated and observed galaxies at all scales, from dwarf galaxies to galaxy clusters, is one of the most active areas of observational and theoretical cosmology, and it represents one of the most promising avenues for learning about the fundamental nature of dark matter, even before a dark matter particle is directly detected. Mystery. 29. Gravitational waves. On September 14, 2015 at 09:50:45 Universal Time, the two LIGO detectors in Louisiana and Washington simultaneously registered a signal lasting approximately 0.2 of a second. The signal swept upward in frequency from about 35 Hz to roughly 150 Hz, briefly reaching a strain, a fractional change in the distance between the detector's mirrors of about 1 part in 10 to the 21st. This is equivalent to measuring a change in distance of 1/10,000th the diameter of a proton across the 4-kilometer length of the LIGO detector arms. The signal was a gravitational wave, a ripple in the curvature of space-time itself, produced by the merger of two black holes approximately 36 and 29 times the mass of the Sun, at a distance of about 1.3 billion light-years from Earth. The merger had released in approximately 0.2 of a second more power than all the stars in the observable universe combined. The signal had been traveling through space for 1.3 billion years before arriving at Earth. The detection was the first direct observation of gravitational waves, confirming a prediction Einstein had made a century earlier, and it launched the era of gravitational wave astronomy, an entirely new way of observing the universe that detects not light or other electromagnetic radiation, but distortions in the fabric of space-time itself. Unlike electromagnetic observations, which measure the behavior of matter and radiation at the source, gravitational wave observations measure the dynamics of mass itself, the motion of massive objects, the curvature they create, the waves they radiate as they accelerate. The sources that gravitational wave detectors have so far observed, binary black hole mergers, binary neutron-star mergers, possible neutron-star-black hole mergers, represent the most energetic events in the universe after the Big Bang itself. Each merger is a brief event of extraordinary violence, two compact objects spiraling together over millions of years, finally merging in milliseconds, releasing more energy in the final moments than the Sun will produce in its entire 10 billion-year lifetime. The mysteries that gravitational wave astronomy is now probing are some of the deepest in astrophysics. The mass distribution of binary black holes, how many there are, what masses they have, how they formed, carries information about the formation and evolution of massive stars and stellar pairs. The neutron-star merger, GW170817, detected simultaneously in gravitational waves and electromagnetic emission across the entire spectrum, provided the first direct measurement of the neutron-star equation of state, the speed of gravity, confirming it equals the speed of light to extraordinary precision, and the origin of heavy elements, gold, platinum, and the other R-process elements are produced in neutron-star mergers, and GW170817 directly confirmed this. Future gravitational wave detectors, the European Einstein Telescope and the American Cosmic Explorer, designed to be far more sensitive than current LIGO Virgo detectors, will extend the reach of gravitational wave observations to cosmological distances, detecting binary mergers from the earliest epochs of cosmic history, potentially including primordial gravitational waves from the inflationary era itself. The space-based LISA mission, expected to launch in the 2030s, will detect gravitational waves at much lower frequencies than ground-based detectors, including signals from supermassive black hole mergers in distant galaxies and from millions of binary star systems throughout the Milky Way. We are at the beginning of gravitational wave astronomy. The universe has always been vibrating. Massive objects have always been merging and radiating. But humanity only gained the ability to hear these vibrations a decade ago. What will be found as the sensitivity and reach of gravitational wave detectors improves is genuinely unknown. The surprises that electromagnetic astronomy routinely produces, unexpected sources, unexpected behaviors, phenomena no one anticipated, will almost certainly have their gravitational wave equivalents found in data that will be collected in the coming decades. Mystery 30. The beginning before the beginning. This is the mystery that underlies all others. Every other mystery in tonight's collection concerns specific features of the universe as it exists, its content, its structure, its history, its future. This one concerns the universe's most fundamental circumstance, that it exists at all, and that it has the specific properties it has, and that those properties permit the existence of structure and life and the questions being asked about them. The Big Bang is the scientific framework for the origin of the observable universe. The evidence for a hot, dense, early state from which the current cosmos evolved is overwhelming. The cosmic microwave background, the abundances of light elements produced in the first 3 minutes, the observed expansion of the universe, the large-scale structure consistent with the primordial density fluctuations amplified over billions of years. The Big Bang is not in question. What is in question is what the Big Bang was. What it was the beginning of, whether it had a cause, and whether the question of what came before it is meaningful or is a category error. In the simplest version of Big Bang cosmology, the universe began in a singular state of infinite density, a mathematical point where the equations of general relativity break down. This is the initial singularity, and it represents the formal beginning of space and time as described by the theory. If time itself began with the Big Bang, then the question, what came before, may be as meaningless as asking what is south of the South Pole. There is no before, not because something preceded the Big Bang and cannot be known, but because the temporal ordering that before implies did not exist prior to the Big Bang. But this answer is unsatisfying in a specific way. It relies on taking the equations of general relativity seriously at conditions where we have every theoretical reason to believe they break down, where quantum gravity effects are dominant, and where a complete theory of quantum gravity is needed to describe what happens. The initial singularity is not a prediction of physics at its most complete. It is a prediction of an incomplete theory applied outside its domain of validity. When quantum effects are incorporated, when you try to ask what happens at and before the Planck era, the first 10 to the minus 43 seconds when quantum gravity is dominant, a range of different scenarios emerge. In the no-boundary proposal of Hawking and Hartle, the universe has no initial singular boundary in time. Instead, time becomes effectively imaginary near the beginning in a mathematical sense, meaning that what appears as a temporal dimension gradually transforms into a spatial dimension, so that the beginning of the universe resembles the south pole of a sphere, a specific location in a smooth geometry without an edge or boundary. In this picture, asking what preceded the universe is indeed meaningless, but for more sophisticated reasons than the simple argument. The universe is finite, but unbounded in time, in the same way that Earth's surface is finite, but unbounded in space. In the cyclic models, including various versions of the ekpyrotic universe and the conformal cyclic cosmology proposed by Roger Penrose, the Big Bang is not the absolute beginning, but a transition between cosmic epochs. In the ekpyrotic model, our universe results from the collision of two higher dimensional branes in a higher dimensional space, and this collision may recur cyclically. In conformal cyclic cosmology, the universe cycles through aeons, each beginning with a Big Bang and ending in an infinitely expanded, cold, dead universe whose structure is conformally related to the initial state of the next aeon. In loop quantum cosmology, which applies the framework of loop quantum gravity to cosmological initial conditions, the initial singularity of classical general relativity is replaced by a quantum bounce, a moment of maximum density followed by expansion from a preceding contracting phase. The bounce cosmology represents a universe that passed through a phase of contraction, reached a minimum size determined by quantum effects, and rebounded into the current expansion. This avoids the singularity but raises questions about the contracting phase and what preceded it. All of these frameworks are theoretical and partially speculative. None has produced a definitive, unique prediction that distinguishes it from the others and from the simplest Big Bang picture in a way that current observations can test. The question of what happened at and before the Big Bang is therefore genuinely open, not in the sense that it is a question science cannot pursue, but in the sense that no current scientific theory answers it with sufficient empirical support to be adopted as the established picture. What makes this mystery different in character from the others is that it encompasses all of them. The specific values of the physical constants, the matter-antimatter asymmetry, the initial low entropy of the universe, the amplitude of the primordial density fluctuations, All of these properties of the universe as we observe it must, in a complete theory of cosmic origins, emerge from or be explained by whatever the universe's beginning truly was. The mystery of the beginning is not one mystery among 30. It is the mystery that all 30 depend on, the question that sits at the foundation of all the others, the deepest question that science has ever seriously posed. And it remains, at this moment in human history, unanswered. 30 mysteries, and the night sky looks the same as it always has. That is perhaps the most unsettling thing about all of this. The universe described by modern cosmology and physics, dominated by dark matter and dark energy, possibly one of infinitely many universes, governed at its most fundamental level by equations that remain partly incompatible with each other, timed to end in a darkness of gradually cooling stellar remnants across timescales that make human history a vanishingly brief episode, is not a universe that looks any different from the stars over our heads. The same sky that ancient people read as the dwelling places of gods, that navigators used as a map, that poets have written about in every language and every era, is the sky that contains all of these mysteries simultaneously. The stars look steady. They have been looking steady for all of recorded history. And yet they are nuclear furnaces held together by a balance between gravity and radiation pressure that produces temporary stability on timescales that dwarf human civilization. The darkness between them is filled with dark matter we cannot see, dark energy we cannot explain, gravitational waves we can only just detect, cosmic rays arriving at energies that should be impossible, and fast radio bursts lasting milliseconds that release more energy than the sun produces in days. The galaxy we call home, 100 billion stars in a flat rotating disk roughly 100,000 light-years across, is itself a minor member of a local group of galaxies, which is itself a minor excursion from the Virgo cluster, which is itself a small node in the cosmic web of filaments and voids that constitutes the large-scale structure of the observable universe. And the observable universe is the portion of total cosmic reality bounded by the cosmic event horizon, the sphere from which light has had time to reach us, which may or may not encompass all of physical reality, depending on whether inflation produced a multiverse or not. We do not know what dark matter is. We do not know what dark energy is. We do not know how the universe's matter-antimatter asymmetry was produced. We do not know what happens inside a black hole. We do not know whether the multiverse is real. We do not know whether we are alone in the cosmos. We do not know why there is something rather than nothing. These are not temporary gaps in a nearly complete understanding. They are genuine, deep, structural questions about the nature of reality that the most powerful physics and astronomy ever developed has not been able to answer. Modern science has done something extraordinary. It has mapped the universe to the precision of the cosmic microwave background, detected gravitational waves from black hole mergers a billion light-years away, imaged the shadow of a black hole at the center of a galaxy, found thousands of planets orbiting other stars. These achievements are real and they are extraordinary. And in achieving them, science has revealed a universe that is vastly more mysterious than anyone expected it to be. That is not a failure. That is how science works at its best. Following the evidence, accepting the uncertainty, staying with the questions long enough to understand how deep they go. The mysteries are not closing, they are opening. Every generation of scientists inherits a universe more strange and more interesting than the one the previous generation thought they understood. Tonight, in the quiet and the dark, all of it is out there. The web of galaxies, the invisible dark matter halos, the accelerating expansion, the millisecond radio bursts from distant galaxies, the black holes that evaporate over unimaginable timescales, the neutron stars spinning dozens of times per second, the ancient photons from the Big Bang washing across the sky in every direction, the possibly habitable planets orbiting other stars, the question of whether any of them have anyone looking back. It is a large universe, it is a strange one, and the part of it we understand is smaller than we thought. Sleep well. The mysteries are patient. They will still be there when the morning comes. The cosmic web itself rewards one more moment of attention before we move away from it. The specific structure of the web, the way filaments connect at nodes of dense galaxy clusters surrounding vast empty voids, is not merely a feature of the universe's large-scale architecture. It is a diagnostic tool for the fundamental physics governing cosmic evolution. The statistical properties of the cosmic web, how long the filaments are, how many there are per unit volume, how dense the nodes are, how empty the voids, depend in specific ways on the amount of dark matter, the nature of dark energy, the neutrino masses, and the amplitude and spectrum of the primordial density fluctuations seeded by inflation. Mapping the cosmic web with increasing precision is one of the primary goals of current and future galaxy surveys. The Euclid Space Telescope, launched in 2023, and the Vera-Rubin Observatory beginning operations in the mid-2020s, will map hundreds of millions of galaxies across large volumes of the universe, providing a three-dimensional portrait of the cosmic web from the present epoch back to a redshift of several, when the universe was a few billion years old. The statistical analysis of this portrait, compared with predictions from cosmological simulations, will provide some of the most precise constraints ever obtained on the fundamental parameters of the universe. What is particularly interesting about the cosmic web as a research tool is that it is sensitive to physics that affects the growth of structure over time. Dark energy affects how fast structure grows. A universe with stronger dark energy expands faster, diluting the gravitational attraction that builds structures, producing a less developed cosmic web at late times. Modified gravity theories that mimic dark energy's effect on the background expansion can sometimes be distinguished from true dark energy by their different effects on structure growth. Neutrino masses. The neutrino is the only particle in the Standard Model whose mass is known to be non-zero, but whose actual mass value is not determined by particle physics experiments alone, suppress structure growth on small scales in a specific way that future surveys will be sensitive to. The cosmic web is not merely a beautiful structure to contemplate. It is a fossil record of the physical processes that shape the universe, encoded in the three-dimensional distribution of matter across cosmic scales. Reading that record accurately is one of the central challenges of 21st century cosmology. Dark matter deserves one more consideration that the initial discussion did not fully address: the astrophysical evidence from systems that dark matter models find most challenging. The bullet cluster is often cited as the most direct evidence for dark matter's existence and for the fact that it truly does not interact strongly with itself or with ordinary matter. The bullet cluster is a system of two galaxy clusters that have passed through each other. Ordinary matter, the hot gas that makes up most of the ordinary mass of galaxy clusters, was slowed by electromagnetic interactions during the collision, trailing behind the galaxies like the shock front behind a supersonic bullet. The dark matter halos, being non-interacting, passed through each other essentially unimpeded, now flanking the gas cloud on either side. Gravitational lensing maps of the bullet cluster show that the mass concentrations, traced by how much the cluster's gravity bends the light of background galaxies, follow the galaxies and dark matter, not the ordinary gas. The mass is where the dark matter should be, not where the ordinary matter ended up after the collision. This provides a visual, direct demonstration that there is more mass in the system than can be accounted for by the visible ordinary matter, and that this extra mass did not interact during the collision, exactly what dark matter predicts. The bullet cluster is one of the most compelling astrophysical arguments for dark matter's existence and for its non-interacting nature. It is not a proof. Science does not work by proof in the geometric sense, but it is strong, direct evidence that has been used to severely constrain alternative gravity theories. Systems like the bullet cluster are difficult to explain without invoking some form of dark matter. The Hubble tension, meanwhile, represents a situation that is genuinely new in cosmology, a persistent disagreement between two different ways of measuring the same quantity, both using well-understood physics and carefully characterized instruments, that has not yielded to systematic error explanations despite years of investigation by multiple independent groups. This is the kind of disagreement that historically has often preceded major advances in understanding. The most exciting possibility for physics, if not for the immediate convenience of theorists, is that the Hubble tension is real and reflects new physics in the early universe. If the pre-recombination universe, the universe before the cosmic microwave background was released, when it was filled with a hot plasma of electrons and photons, contained some additional component that affected the expansion rate at that time, this could shift the apparent distance scale inferred from the cosmic microwave background and bring the two Hubble constant measurements into agreement. Early dark energy, a component that made a brief contribution to the energy density before recombination and then rapidly became negligible, is one of the more developed proposals for this kind of solution. The implications would be significant. Additional components in the early universe affect not only the Hubble constant, but other cosmological observables. The amplitude of baryon acoustic oscillations, the sound horizon scale, the matter power spectrum. And any proposed solution must improve the Hubble tension without worsening the fit to these other measurements. Finding such a solution has proven difficult, and current proposals either fail this test or make only partial progress. But the problem is young enough and the physics rich enough that a solution remains plausible. The FRB story is also still developing. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, began operations in 2018 and has dramatically increased the rate of FRB discovery, detecting hundreds of events and particularly excelling at identifying repeating sources. CHIME's systematic all-sky survey approach has revealed that repeating and apparently non-repeating FRBs have different statistical properties, different burst widths, different spectral shapes, that hint at physical differences in the sources or the emission mechanisms, even if all originate from magnetars or similar compact objects. One of the most intriguing repeating FRB sources is FRB 121102, the first repeater detected, which is located in a dwarf galaxy about 3 billion light-years away, and is associated with a persistent radio source and what appears to be an environment of extreme magnetic field strength, consistent with a young magnetar embedded in a dense nebula. The periodicity of some repeaters, some show a preferred period at which bursts are most likely to occur, consistent with precession or orbital modulation of the emission beam, adds structure to what initially seemed like random activity. What FRBs will ultimately tell us about their sources, about the intergalactic medium, and about fundamental physics will emerge gradually as the sample grows and as new instruments like the Square Kilometre Array come online with orders of magnitude improvements in sensitivity and sky coverage. The FRB field is less than 2 decades old and is already one of the most rapidly developing areas of observational astronomy, and the gravitational wave sky continues to fill in. As LIGO and Virgo have accumulated more events, the population of binary mergers has grown rich enough to test astrophysical models of binary formation and stellar evolution. Questions that seemed purely theoretical, how do stellar mass black holes pair into binaries? Do they form in stellar clusters or in isolated binary star systems? Are there gaps in the mass distribution of compact objects that reflect the physics of supernova explosions? Are now being answered observationally as gravitational wave events accumulate. The answers being produced are not always what the models predicted, and the surprises are where the science is. The Pioneer anomaly resolution, the finding that a decades-long puzzling spacecraft trajectory discrepancy was ultimately caused by thermal radiation pressure, contains a lesson that runs through several of tonight's mysteries. The most unsatisfying scientific situation is not genuine mystery but apparent mystery that persists because of incomplete analysis rather than genuinely unknown physics. The Pioneer anomaly fell in that category. The Hubble tension may not. The analyses have been checked extensively enough that systematic error is becoming increasingly implausible. The wow signal may never be resolved because it has not repeated, and because the data that exists is finite and the source silent. The difference between these situations is not always obvious from the outside, and distinguishing them requires the kind of careful, systematic analysis that takes years and enormous scientific effort. The search for biosignatures in exoplanet atmospheres is a domain where the distinction between genuine biological signatures and abiotic chemistry will be extraordinarily difficult to establish even after a candidate biosignature is detected. The history of claimed biosignatures is cautionary. The Martian meteorite ALH 84001, announced in 1996 as potentially containing evidence of ancient Martian microbial life in the form of mineral structures and organic molecules, has been debated for decades without resolution. The structures are real, the organics are real, but the biological interpretation is not generally accepted. The phosphine claimed to have been detected in Venus's atmosphere in 2020 as a possible biosignature was subsequently disputed, with alternative explanations proposed for both the signal itself, which may have been a calibration artifact, and for the phosphine's origin if the signal were real, abiotic, volcanic, or chemical processes. These episodes illustrate how difficult the inference from chemical observation to biological conclusion actually is. What is remarkable about the current moment in exoplanet science is not that biosignatures have been found, they have not, but that the tools now exist to look for them systematically and with meaningful sensitivity. James Webb can detect the presence of methane and carbon dioxide in the atmosphere of a planet 120 light-years away. In the next decade, planned instruments will extend this reach to smaller, rockier planets around Sun-like stars and to a wider range of chemical species. The search is real and it is underway, and its null results as well as any positive results will provide genuine information about the prevalence of life in the universe. The neutron star equation of state problem illustrates a different kind of scientific situation, one where the relevant physical conditions are extreme enough that experiments on Earth cannot directly test the theory. The highest densities achievable in terrestrial experiments, in heavy ion collisions at particle accelerators, are extreme, but neutron star cores are denser, and the specific regime relevant to neutron star interiors is poorly constrained by laboratory measurements. Astrophysical observations of neutron stars therefore serve as the primary experimental window onto this regime. Gravitational wave measurements of neutron star mergers, X-ray observations of neutron star surfaces and interiors through space telescopes like NICA, and radio timing observations of pulsars all contribute constraints on the equation of state from different directions. The picture is becoming clearer, but the specific question of whether quark matter exists in neutron star cores remains open. Inflation, the proposed period of exponential expansion in the early universe, sits in an interesting scientific position. It is well motivated as a solution to specific cosmological puzzles, and it makes predictions that have been confirmed. But the space of inflationary models is large, and distinguishing between them observationally is difficult. The detection of primordial B-mode polarization in the cosmic microwave background, the gravitational wave imprint of the inflationary era, would be one of the most important results in observational cosmology if achieved. Current experiments, including the BICEP Keck array at the South Pole and the Simons Observatory now being built in Chile, are pushing the sensitivity frontier on this measurement. A detection at a level consistent with the simplest inflationary models, those predicting the highest gravitational wave amplitudes, would confirm not just that inflation happened, but that the energy scale at which it happened was specifically high. An upper limit that definitively excludes all simple inflationary models would be a crisis for the theory. The question of whether space-time is fundamental or emergent is one that may be answered, if it is answered not by a single dramatic experiment, but by the gradual convergence of theoretical insights and observational constraints from multiple directions. Quantum gravity phenomenology, gravitational wave observations, black hole physics, and the precision tests of quantum mechanics that are becoming possible in increasingly large and complex quantum systems. The emergence of spacetime from quantum entanglement, if it is real, may leave signatures in gravitational wave signals from black hole mergers, in the specific behavior of Hawking radiation, if it is ever observed in an analog system, or in the statistics of quantum systems in ways that current theory is only beginning to explore. These are young ideas in an old universe. 30 mysteries, and the oldest of them, why is there something rather than nothing, is as young a question today as it was when the first philosopher articulated it. The universe has been here for 13.8 billion years, Human beings with the capacity to ask scientific questions about it have been here for perhaps 100,000. The particular forms of scientific inquiry that have produced the picture described tonight have been here for 400 years, and the specific tools, the radio telescopes, the gravitational wave detectors, the space observatories, for decades. The universe is patient. It has been keeping its secrets in plain sight for billions of years, answering them gradually to the small populations of curious creatures that have evolved in its midst. Every generation of those creatures has found the universe stranger and larger and more surprising than the previous generation expected. There is no particular reason to think the current generation has reached the end of the surprises. Tonight, the sky above you contains all of this. The dark matter that shapes every galaxy you will never see. The dark energy that is slowly pulling the observable universe apart. The gravitational waves from black hole mergers that pass through Earth during today and yesterday and every day of human history, imperceptibly deforming the length of everything by amounts smaller than any physical instrument could have detected until 10 years ago. The cosmic microwave background photons, the oldest light in the universe, arriving from every direction at every moment. The sky looks the same as it always has, but it is not what it appears to be, and we know that now. We know it is stranger and larger and fuller of mystery than our senses suggest. And that knowledge, the specific knowledge of how much remains unknown, is one of the most remarkable things human beings have ever managed to achieve. Sleep well. The universe is watching. The story of how dark energy was discovered deserves a moment of additional attention, because it is one of the most counterintuitive episodes in the history of observational astronomy. The two teams competing to measure the deceleration of cosmic expansion in the late 1990s, the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt with Adam Rees as the lead analyst, were not looking for acceleration. They expected to find deceleration. The entire point of the exercise was to measure how much deceleration there was, because the answer would tell you the density of matter in the universe and determine the universe's ultimate fate. A matter-dominated universe would decelerate, and the more matter, the faster the deceleration. The teams wanted to measure the deceleration parameter. When the data came in and both teams independently found that distant supernovae were dimmer, farther away, than any plausible deceleration model predicted, the initial response was to look for systematic errors. Something might be wrong with the calibration of the brightness of Type Ia supernovae at high redshift. There might be dust absorbing some of the supernova light and making them appear dimmer. There might be a population of Type Ia supernovae at high redshift that had different intrinsic luminosities from the nearby supernovae used for calibration. Each of these possibilities was examined carefully. None of them could account for the full observed effect. The conclusion was forced. The expansion of the universe is accelerating. Something with negative pressure, something acting like a repulsive force distributed throughout space, is overwhelming gravity on the larger scales and causing the expansion to speed up. This something has been called dark energy because it is dark, undetected by any other means, and energetic. It constitutes the dominant component of the universe's energy density. The discovery was awarded the 2011 Nobel Prize in Physics to Perlmutter, Schmidt, and Rees. It was a result that nobody had anticipated, that violated the expectations of essentially every cosmologist working at the time, and that required a complete revision of the standard cosmological model. In retrospect, there were hints in the data on galaxy clustering and the cosmic microwave background that the universe was not matter-dominated in the way that would produce deceleration. But those hints were not clear enough to generate the specific prediction that the expansion was accelerating. The supernova teams found what they found, and it changed cosmology permanently. The neutrino is itself one of the strangest particles in the standard model of particle physics, and its properties bear on several of tonight's mysteries in ways that are worth making explicit. Neutrinos are produced in enormous quantities by nuclear processes. The Sun produces about 2 × 10 to the 38th neutrinos per second, and approximately 65 billion solar neutrinos pass through every square centimeter of Earth's surface every second. They interact so weakly that essentially all of them pass through Earth without stopping. The planet is transparent to neutrinos. The same is true of your body and of any material you might try to use as a shield. Yet neutrinos are not entirely without influence on the universe. The total mass of the universe is neutrinos, while tiny per individual particle is cosmologically significant because there are so many of them. Neutrino masses affect the formation of cosmic structure. Because neutrinos travel at nearly the speed of light in the early universe, they stream out of overdense regions and suppress the growth of small-scale fluctuations, leaving a specific imprint on the power spectrum of galaxy clustering. Current cosmological observations constrain the sum of neutrino masses to be less than about 0.12 electron volts, a mass scale that particle physics experiments alone have not yet reached. Future galaxy surveys will constrain the neutrino mass sum to even smaller values, potentially reaching the level where the minimum neutrino mass predicted by oscillation experiments, which establish that at least some neutrinos have masses above a certain threshold, can be directly detected in the large-scale structure of the universe. The neutrino mass is one of several places where cosmological observations are more sensitive than direct particle physics experiments, where the universe itself serves as the most powerful laboratory available for fundamental physics. Dark matter properties, the equation of state of dark energy, the primordial power spectrum from inflation, the neutrino mass. All of these fundamental physics quantities are being measured or constrained through astronomical observations, supplementing and in some cases surpassing what can be done in particle accelerators. This convergence between cosmology and particle physics is one of the defining features of contemporary fundamental science. Consciousness, though the last of the scientific topics we touched on in the main list, is the one where the scientific situation is most uncertain and where the risk of overreaching in either direction is greatest. The mainstream scientific position is that consciousness is a product of certain types of information processing in physical systems, that it has a physical basis in the brain, and that its relationship to quantum mechanics is purely incidental. Quantum effects in neurons, if present at all, do not play a special functional role in cognition. This position is not dogma, it is the conclusion of the majority of neuroscientists and philosophers of mind who have studied the question carefully, in a situation where certainty is not available. The minority position are that consciousness plays a more fundamental role in physics, or that it cannot be fully accounted for by the standard physical picture, is not scientifically dead, but it faces the problem that no experiment has produced evidence favoring it over the majority position. The hard problem of consciousness, the problem of explaining why any physical process gives rise to subjective experience at all, is a genuine philosophical puzzle that has not been resolved. But the existence of an unresolved philosophical puzzle does not by itself constitute evidence for any particular physical theory. What cosmology adds to this discussion is the observation that consciousness appears to be rare in the universe. Even if life is common, intelligence seems to require specific conditions and long timescales, and the conditions currently prevailing in the universe, an era of active stars, stable planetary systems, complex chemistry, will not persist indefinitely. If consciousness is a product of physical complexity of a specific kind, then its prevalence in the universe is a function of how often those physical conditions are achieved. And the answer to that question is what the various lines of investigation describe tonight. The exoplanet atmospheric surveys, the search for biosignatures, the models of planetary formation and habitability are trying to determine. The universe is proceeding on its own timeline, indifferent to these investigations. Galaxies continue their slow migrations through the cosmic web. New stars ignite inside molecular clouds. Old stars shed their outer layers into the interstellar medium, enriching it with the elements that future rocky planets and living organisms will be built from. Black holes at the centers of galaxies consume infalling matter, briefly illuminating the surrounding gas with quasar luminosities, then dimming again as the gas is depleted. Neutron stars spin down over millions of years, their powerful magnetic fields gradually weakening, transitioning from pulsars to quieter magnetars to cold, dark remnants. Gravitational waves from compact object mergers propagate outward at the speed of light, crossing the emptiness between galaxies in pulses of space-time curvature that carry encoded information about the most violent events in the accessible universe. And across all of this, across the entire observable universe, from its hot beginning to its cold, probable end, the questions we have asked tonight persist as genuinely open. We do not know what dark matter is. We do not know what dark energy is. We do not know how the universe's matter-antimatter asymmetry was produced, or what inflaton field drove cosmic inflation, or what happened at the Planck era before the equations of known physics break down. We do not know whether there is life elsewhere in the universe, or whether the WOW signal had an intelligent source, or what fast radio bursts ultimately tell us about the physics of extreme compact objects. We do not know what happens inside a black hole, or whether information is genuinely preserved in Hawking radiation, or what the underlying structure of space-time looks like at the Planck scale. 30 mysteries, and each of them is a real question with a real answer that the universe knows and that we do not yet know. The answers are there in the physics of the universe, in the behavior of matter and energy across scales from the subatomic to the cosmological. They are not hidden by any intelligence or kept secret by any agency. They are simply not yet discovered, waiting for the next observation, the next experiment, the next theoretical insight, the next generation of scientists who will look at the available evidence with fresh eyes and find the pattern that was not visible before. That is the specific promise of science, and it is a promise that the universe has kept remarkably well across 4 centuries of systematic inquiry. The answers are out there. Some of them will be found in the coming decades. Some will take longer, and some perhaps will reveal new mysteries beneath them that we have not yet imagined. The sky is full of questions. They have been waiting patiently for us, and they will wait with the patience of the cosmos until we are ready to answer them.